Hello there, and welcome to Physics with William, where we take difficult ideas, slow them down, and let them sit quietly for a while so they can make sense without demanding too much of a tired brain. Tonight we are turning our attention to something that is all around you already. It is in the screen you may be watching right now, in the lamp across the room, in the last trace of daylight that may still be hanging outside your window, and in the old starlight that has spent years crossing space only to arrive, very politely, in your eyes. We're going to spend some time with a question that sounds small at first, and then gets stranger the longer you hold it. What happens inside a photon? That is a curious question, because a photon is one of those scientific words that can feel both familiar and remote at the same time. People hear it and think of textbooks, laboratories, and perhaps one very determined teacher with a laser pointer. But a photon is not locked away in a classroom. It is involved in nearly everything you see. Every colour on a flower, every glow from a street lamp, every shadow on a wall, every sunset that turns ordinary clouds into something worth stopping for. All of it depends on light. And light, as far as our best physics can tell, comes to us in photons. Now, before we get too serious, I should ask a small question that suits the subject rather nicely. Where are you listening from tonight, and what is the light like where you are? Is it morning where the room is still cool and the day has not fully started? Is it evening with that familiar tired softness that makes every lamp feel slightly more important? Is it the middle of the night with only a little glow from a screen and maybe a hallway bulb doing its best? However it looks around you, however bright or dim, there are photons involved in every part of it, arriving in enormous numbers without ceremony, never knocking, simply showing up and making the world visible. And because this is a long and gentle kind of journey, if you find this soothing or interesting, or simply a decent companion for winding down after a busy day, I would be grateful if you gave the video a like and maybe subscribed as well. It helps this quiet little corner reach more people who enjoy science, delivered at a pace that does not feel like an exam. There is already enough in life that arrives with urgency. Photons do not need to be one more thing. What makes the question so appealing is that it sounds like the sort of thing that ought to have a simple answer. What happens inside a photon? We ask similar things about all sorts of objects. What is inside a clock? Gears and springs, or perhaps a battery and small circuits? What is inside a seed? Cells, stored nutrients, the instructions for roots and leaves. What is inside a raindrop? Water molecules pressed together for a short and rather eventful journey, so it feels reasonable to ask what's going on inside a photon. Is there some tiny engine in there? Some vibrating core? Some little structure that gives it colour and energy and speed? Is a photon a very small object with very small parts, rushing through the universe like a glowing bead with secrets packed into it? Physics, of course, is rarely so cooperative. The trouble begins with the fact that light does not behave the way common sense expects it to behave. Most of us grow up surrounded by objects that sit still when placed on a table, and move only when pushed or thrown. We learn to trust solid things. Cups stay where cups are put. Chairs remain stubbornly chair-shaped. Breadcrumbs fall down rather than sideways. The world of daily life trains us to think in terms of ordinary objects with ordinary sizes and ordinary insides. Then along comes light, and calmly ignores half of those expectations. Light travels through empty space. It arrives from the sun after crossing a vast distance that would make most road trips seem slightly optimistic. It can behave like a wave spreading out, and yet it can also arrive in distinct little packets that transfer energy in very definite amounts. It can be reflected, absorbed, scattered, focused, bent, and split. It can carry information from a distant galaxy, or simply help you locate the kettle in a dark kitchen. It is so useful, so constant, so ordinary in daily life, that we often forget how strange it really is. We treat light as if it were obvious, when in fact it is one of the most successful magic tricks in nature, except that it is not magic, which somehow makes it more impressive. A photon is our name for the smallest unit of light that can be treated as a distinct quantum event. That sentence sounds far more severe than it needs to be, so let's put it in friendlier terms. Imagine you're not dealing with an endless smooth beam of light, but with individual deliveries. Not lumps in the everyday sense, not tiny pebbles of brightness, but discrete bits in the way nature allows light to give and take energy. A photon is one such bit. It is not a miniature marble. It is not a dot with a shell and a centre. It is the basic amount in which light interacts. Already you can feel the question shifting slightly. We started by asking what happens inside a photon, but if a photon is not built like a tiny object with walls and contents, then perhaps the question itself needs adjusting. That is one of the things physics does to a person. You begin with a question that sounds perfectly reasonable, and a few minutes later the universe has gently moved the furniture around. Nothing rude, just enough to make you stop and look again. Still, that is part of the fun, and I do mean fun in the quiet sense, not the kind that requires confetti or loud music. There is something deeply satisfying about realizing that a familiar thing is not simple at all. Take a beam of sunlight falling across a floor. It feels ordinary. You have probably seen it 1,000 times. But hidden in that ordinary scene is a procession of photons arriving after a long trip from the sun, each one tied to processes inside a star so intense that even thinking about them from the comfort of a chair feels slightly unfair. Or take the light from a candle. It looks gentle enough, almost modest. Yet the glow you see depends on atoms, energy changes, and the emission of photons in ways that would have sounded absurd to much of human history. The everyday world is full of advanced physics behaving itself so well that we stop noticing. Part of the reason the topic matters is that photons are not a side note. They are central characters in the story of modern science. They help explain why we see, how stars shine, how plants gather energy, how solar panels work, how information moves through fibre optic cables, how atoms absorb and emit light, and how we probe the structure of matter itself. If you remove photons from the picture, the world does not merely get darker. Huge portions of physics, chemistry, biology, and technology become impossible to describe properly. It would be like trying to explain a city without mentioning roads, and yet photons remain difficult to picture. They resist the kind of mental image we like to build. A planet is easy enough to imagine. Even an atom, though not pictured accurately in school diagrams, at least offers the mind something to hold. A photon is more slippery. The closer you try to pin it down as a little object, the more the description begins to fail. The more you spread it out as a wave, the more you risk losing the sense in which it arrives and interacts in individual events. It is not that science has no answer. Science has a very good answer. It is simply not an answer built for the instincts we developed while carrying groceries and avoiding table corners. There is also something wonderfully humbling about light when you pause to consider it. Long before humans knew what a photon was, long before lenses, telescopes, quantum theory, or laboratory equipment, light was already doing its work. It warmed skin. It guided migration. It signaled morning. It painted seasons onto landscapes. It told leaves when to grow and eyes when to wake. Whole civilizations studied its behavior without having the language we now use. They tracked shadows, watched dawn, marked solstices, built monuments to catch certain kinds of light at certain times of year. They did not speak of photons, but they were paying close attention to what photons do. That history matters because it reminds us that knowledge usually begins in observation before it graduates into theory. Someone notices that light bends through water. Someone else notices that colours separate in glass. Someone notices that sunlight can feel warm, and yet moonlight, though visible, does not do the same job. People notice brightness, shadow, reflection, sparkle, glare. Then slowly, over generations, the observations accumulate. Instruments improve, language sharpens, questions become more precise. Eventually you get to a point where asking what happens inside a photon becomes possible at all. It is also worth admitting that the question contains a quiet trap, and it is a trap our brains set because they prefer familiar categories. When we hear the word inside, we assume boundary. If something has an inside, it must also have an outside. If it has an outside, it must have shape. If it has shape, it must occupy a clear little volume the way a grain of sand or a drop of oil does. But the quantum world is not always willing to honour those assumptions. The vocabulary of ordinary objects begins to wobble when used too literally. A photon is real. It is measurable. It has effects that can be tracked with exquisite precision. But that does not mean it possesses the kind of inside that a suitcase or a plum possesses. Now that may sound as if the whole topic is about to dissolve into a fog of technical caution, and I promise that is not the plan. We are not here to hide behind difficult words and call it depth. The goal is much simpler. We want to understand what a photon is well enough that the original question becomes richer, not poorer. Because sometimes the best scientific progress is not finding a quick answer. It is learning why the quick answer does not quite work and then replacing it with something better. Think of it this way. If a child asks what is inside a rainbow, you could say droplets, light, colour separation, wavelengths, optics. Those are all useful pieces. But the deeper lesson is that a rainbow is not an object sitting out there waiting to be peeled open. It is an event, a relationship among light, water, angle, and observer. The question becomes clearer once you stop treating the rainbow like a painted arch and start understanding the process that makes it appear. In a similar way, asking what happens inside a photon may eventually lead us to ask a more powerful question. Not what is hidden at its centre, but what kind of thing a photon is, how it comes into being, how it carries energy, how it behaves in motion, and how it changes what happens when it meets matter. That is where tonight's topic becomes especially interesting. Because photons do not merely reveal other things, they are themselves clues. They tell us that nature is not built only from solid bits banging together like billiard balls. They tell us that energy can come in discrete amounts. They tell us that particles and waves are not always rivals, but sometimes two ways of describing behaviour that does not fit neatly into either everyday box. They tell us that emptiness is not simple, that motion at the deepest levels is not intuitive, and that our best understanding of reality depends on concepts that would have sounded impossible before the 20th century. There is also something delightful about the scale of the matter. A photon is not heavy. In fact, it has no rest mass at all, which is one of those scientific statements that sounds dry until you realise how dramatic it is. A thing with no rest mass still carries energy, still carries momentum, still can push, trigger, heat, reveal, and transform. Light from the sun can warm the surface of your skin. Light in a laser can cut material. Light arriving at your eye can produce vision. Light from a distant supernova can tell us about an event that happened long before any person on Earth saw it. All of that, and still the basic unit of the process refuses to behave like an ordinary tiny object with an ordinary tiny inside. You may have noticed that this is one of the reasons physics becomes addictive to certain minds. Not because it offers grand speeches about mystery, but because it keeps turning ordinary experience into a set of precise surprises. A lamp looks simple until you ask how it shines. Colour looks obvious until you ask what it means physically. Seeing feels immediate until you ask what, exactly, entered your eye. Even darkness becomes more interesting once you realise it is not a thing in itself, so much as a condition in which fewer photons are reaching you. The room does not fill with darkness the way a bowl fills with soup. The arrivals simply dwindle, and then there is the personal side of it. Every visible memory you have is tied to photons. The face of someone you care about, the colour of a childhood room, rain on pavement at night, the bright and rather suspicious lighting of supermarket aisles, the first glimpse of the sea on a trip, dust in a sunbeam, headlights in fog, snow under street lamps. All of those moments reached you through light, not in the vague sense that things were illuminated, but in the very literal sense that photons interacted with the world, bounced or scattered or streamed from it, and ended their journeys by triggering events inside your eyes and brain. A photon is small in one sense, but it takes part in nearly every visible memory you've ever formed. That alone makes the subject worth lingering over. We are not studying some remote curiosity with no place in ordinary life. We are studying one of the main ways reality introduces itself to us. The universe, for the most part, does not hand us objects directly. It sends light. We infer the rest. So when we ask what happens inside a photon, we are really standing at the edge of several connected questions. What is light at its most basic? How can something act like both a wave and a particle depending on the situation? How is a photon produced? What properties does it carry? How does it move through empty space? What happens when it reaches an atom, a mirror, a leaf, a camera sensor, or the back of your eye? And perhaps most importantly for where we're going next, does it even make sense to imagine a photon as having an inside in the everyday physical sense? That is the point at which the simple sounding question becomes properly useful, because the answer is not going to begin with a list of parts tucked into a tiny shell. It begins by realizing that a photon is not a little box of light with machinery hidden in the middle. To understand what happens in a photon, we first have to understand what sort of thing a photon is supposed to be at all, and why the language of insides and outsides starts to mislead us just when the subject is becoming interesting. The first thing to do is to loosen our grip on the image most people naturally form when they hear the word particle. It is almost impossible not to picture something like a tiny bead, a dust grain, a speck so small that no microscope could catch it, but still a little object in the everyday sense. We imagine a surface, a centre, perhaps layers, perhaps hidden mechanisms, perhaps a compact little interior where the real business is done. That habit is understandable. It comes from spending a lifetime around things that do have insides. A loaf of bread has an inside, a watch has an inside, even a pebble has a structure if you cut into it far enough. So when physics tells us that light can behave like particles, the mind quickly reaches for the nearest familiar picture and builds a miniature object out of it. That is where the trouble begins, because a photon is not a little bead of light with a shell and a core. It does not have panels you could open, or a dense centre that stores its brightness, or smaller pieces tucked inside like tools in a drawer. When physicists say that a photon is an elementary particle, what they mean is not that it is merely very small. They mean that, as far as our best current understanding goes, it is not made of smaller constituent parts at all. It is not a tiny machine. It is not a container. It is not a composite object waiting to be taken apart. In that very important sense, there is no inside to inspect. Now that can sound a little too neat, as if science has simply declared the matter closed and moved on for tea. But there is a difference between saying we have not found an inside yet, and saying that the concept itself may be the wrong one to apply. With a chair, you can always imagine zooming in, and finding wood fibres, then molecules, then atoms, then smaller components. A chair is built from parts nested within parts. With a photon, the theory itself does not describe that sort of layered construction. A photon is one of the basic excitations of the electromagnetic field. That is the formal way of putting it. In friendlier terms, it is not a little object floating in a field the way a duck floats in a pond. It is more like a localized quantum event of the field itself. Already you can see why the language of insides begins to creak a bit. It helps to notice how often our intuition confuses smallness with structure. If something is tiny enough, we assume it must resemble ordinary objects, only reduced in scale. But shrinking an everyday picture does not always produce a good model. A hurricane is not just a large drain swirl. A thought is not just a small speech. And a photon is not just a tiny glowing marble. Size is not the only question. The deeper question is what kind of thing we are dealing with. If you start from the wrong category, every later detail becomes harder to grasp. There was a time when scientists hoped the microscopic world might eventually become intuitive in the same way as the visible world. Reduce everything far enough, and perhaps all matter and light would turn out to be built from little bits behaving in tidy mechanical ways. There is something appealing about that hope. It promises a universe with sensible furniture. Yet the closer physics has looked, the more it has found that fundamental entities do not always resemble the things that trained our instincts. They are real, measurable, and astonishingly well described by theory, but not especially eager to become little clockwork toys for the imagination. One useful way to think about the problem is to ask what it would even mean for a photon to have an inside. Usually an inside implies at least three things. First, a boundary separating one region from another. Second, an arrangement of content within that boundary. Third, some possibility of probing or slicing the object to reveal deeper structure. All three ideas work well for familiar matter. A peach has skin, flesh, and a pit. A battery has a casing and material within it. A cell has a membrane and internal machinery. But a photon does not come with a surface the way a peach does. It is not made of stuff packed into a volume with a clear outer edge. The theory does not hand us a neat spherical package and say here is the shell and here is the filling. In fact, if you try too hard to picture a photon as a little bullet racing through space, you will soon run into contradictions. A bullet has a rest state. It can sit on a table. It has a shape you can in principle measure from all sides. A photon has no rest state in that sense at all. It is never found sitting still. It is always in motion. That alone makes it very different from the objects our brains prefer to picture. There is no ordinary point of view from which a photon is parked quietly so that we may stroll around it and examine the workmanship. Nature does not offer that convenience. This is one of those cases where physics asks us to let go of an image before replacing it with a better idea. The better idea is not that the photon is unreal or vague or somehow merely mathematical. Quite the opposite. It is that the photon belongs to a class of things whose reality is not best captured by tiny object imagery. It has definite properties. It carries energy. It carries momentum. It can be emitted, absorbed, and detected. It can be counted in experiments. It can trigger a single atom to change state. It can knock electrons free from a material. It can cross immense cosmic distances and arrive with information about where it has been. None of that is fuzzy. The difficulty is not in whether the photon is real. The difficulty lies in choosing a mental picture that does not quietly smuggle in the wrong assumptions. It may help to compare the photon with objects that really do have internal structure. Consider a proton. For a long time, protons were treated as if they were fundamental. Then experiments showed that they are built from smaller constituents. In certain collisions, the proton reveals an internal organization. It can be probed and its substructure inferred. One may speak meaningfully about what is going on inside it, not in the everyday visual sense perhaps, but in the physical sense that it is made of more basic parts whose behavior contributes to the whole. A photon, by contrast, does not currently show evidence of such compositeness. It is described as elementary. That means when we ask what is inside it, the most honest answer is that there is no known smaller architecture waiting there, and yet the mind keeps pushing back, because something this effective feels as though it ought to contain machinery. How else could it do so much? How could it carry energy and momentum, take part in interactions, display polarization, and travel in the way it does, if there is no internal engine? The answer is that these properties do not need to be explained by tiny gears. We are so used to mechanisms being built from smaller moving parts that we forget some properties are fundamental in the theory. A photon does not carry energy because little cogs spin inside it. It carries energy because that is part of what a photon is. Likewise, an electron does not have electric charge because it keeps a charged pebble in its pocket. Charge is one of its basic attributes. Fundamental entities are not always explained by further reduction. Sometimes reduction reaches a level where the properties are simply part of the basic description. This can feel unsatisfying for about 5 minutes, until one realizes that everyday explanations also stop somewhere. Ask why a piano makes sound, and you can be given a mechanism involving strings and vibrations. Ask why vibrations behave as they do in a material, and you go deeper into elasticity and atoms. Ask why atoms have the structure they do, and you descend again. Eventually, every explanation reaches a level where the best answer is not a smaller clockwork, but a more fundamental rule. Physics is not unique in this. It is simply more honest about where the flaw currently lies. There is another reason the phrase inside a photon becomes misleading. A photon is not best thought of as a tiny object with a fixed shape occupying a little private territory in space, the way a seed or a grain of salt does. In quantum theory, what we call a particle can be associated with states that are spread out, localized to varying degrees, and described probabilistically in terms of how interactions occur. A detected photon may arrive in a very specific event, but that does not grant it a little hard shell all the way along its path. It is better understood through the structure of the field and the rules of quantum interaction than through any miniature pebble picture. That may sound technical, but the basic point is not too fearsome. If you throw a tennis ball, the ball remains a familiar object all along the way. It has a surface, an inside, and a clear identity in the everyday sense. If light is sent toward a detector one photon at a time, the results do not invite quite the same picture. The photon can produce localized detection events, yes, but the route from source to detector is described in a way that does not line up with the behavior of a tiny classical ball. So even before asking what is inside it, we have to admit that the object-style picture is already under strain. There is a slightly comic pattern in the history of science where the universe allows us to build a useful intuition, and then, just as we start feeling proud of ourselves, it reveals the intuition was only good within a certain range. Newtonian mechanics works beautifully for apples, planets, pendulums, and buses that are late in very normal ways, but it does not govern the quantum world in a fully adequate way. Likewise, the ordinary picture of small objects with insides works beautifully for beans, batteries, and breadcrumbs. But once you move into the domain of photons, the universe begins clearing its throat. Even language contributes to the confusion. The word particle sounds solid. It sounds like something one might brush off a coat sleeve. If physics had chosen a less tangible everyday term, perhaps fewer misconceptions would follow. But particle has history behind it, and history tends to linger. So we say particle, while also warning that particle in quantum physics does not mean what your hands and eyes learned from pebbles and dust. It means a quantized entity associated with certain kinds of interactions and measurements. That is accurate, though admittedly not the kind of phrase one wants embroidered on a cushion. Still, the reward for accepting this strangeness is that the subject becomes clearer. Once we stop demanding an inside in the everyday sense, we can ask more productive questions. What properties are fundamental to a photon? How do those properties show up in experiments? Why does a photon always move as it does? How can something without rest mass still carry momentum? What does polarization really mean if there is no tiny spinning lamp bulb inside? Why does light come in these quantized interactions at all? Those questions take us closer to the heart of the matter than any attempt to imagine cracking open a photon with a sufficiently determined microscopic can opener. It is also useful to remember that no one has ever seen the inside of anything in the ordinary visual sense at the deepest level. Even when scientists speak confidently about internal structure, they are not peering with tiny eyes into tiny rooms. They infer structure from interaction, scattering patterns, conservation laws, and the predictive success of theory. In the case of the photon, those same methods have not revealed a smaller substructure. The current framework treats the photon as elementary, and it does so with extraordinary success. That does not mean science will never deepen its account. Science has surprised itself before, but it does mean that, right now, the idea of a hidden internal architecture is not something the evidence requires. There is a temptation, when hearing that something has no inside, to imagine it as flatly featureless. But featureless is not quite right either. A photon has no inside in the composite sense, yet it still has character. It has energy linked to its frequency. It has momentum. It has polarization. which tells us something about the orientation of its electromagnetic behaviour in an interaction. It can participate in interference and diffraction. It can be absorbed in one context and pass through another. It can be produced by atoms, stars, hot objects, lasers, and other processes that we have not yet even begun to unpack tonight. So no, it is not a tiny box with contents, but neither is it a blank nothing. It is a fundamental entity with a very specific role in the structure of physical reality. That role becomes even more interesting when we consider how much of the visible world depends on it. Every colour you see comes from photons interacting with matter in particular ways. The blue of the sky, the red of a warning light, the green of leaves, the pale glow of morning through curtains, all of that depends on photons with different energies being emitted, scattered, reflected, or absorbed. The ordinary richness of sight is built not from objects announcing their qualities directly, but from matter selecting and shaping the photons that reach you. If photons had ordinary insides, we might be tempted to imagine colour packed somewhere within them like dye in a bottle. But that too would be misleading. Colour in the physical sense is tied to the energy of the photon and to how visual systems interpret it, not to pigment hidden in a tiny interior. The same is true of brightness. A bright light source is not sending larger photons stuffed with extra shine. It is sending more photons, or photons with energies arranged in ways that produce greater intensity in the detection system, depending on the circumstances. Again and again, the moment we imagine a photon as a tiny object with contents, we begin asking the wrong kind of questions. The reality is subtler and much more consistent. Another comforting thing to note is that not having an inside does not make the photon incomplete. We sometimes speak as though a thing without hidden layers must be lacking something, as if simplicity were a deficiency. But physics does not treat fundamentality as a failure of richness. A photon is not waiting to become more respectable by growing organs. It already sits at a level of description where its properties are basic. In a way, that is a cleaner sort of existence than most objects enjoy. A chair must answer questions about wood, fibres, molecules, atoms, and the forces binding them. A photon has no such domestic burden. It is what it is in the theory, and the theory has so far handled it extraordinarily well. There is, however, one final twist worth lingering on before we move onward. When people ask what happens inside a photon, they're often reaching for a deeper concern without realizing it. They're really asking how something so simple can be so capable. How can a thing with no inside still do work in the universe? How can it be born from matter, travel across emptiness, carry energy, and then vanish into an interaction, as if that were the most ordinary thing in the world? That instinct is good. It points us away from anatomy and toward process. The interesting story is not hidden in a tiny interior chamber. It is found in how photons come into being, what rules govern their behaviour, and how they meet the rest of reality. So perhaps the kindest way to answer the original question is this. Nothing happens inside a photon in the way things happen inside a clock or inside a cell, because a photon is not built from smaller moving parts with an enclosed interior. It is a fundamental quantum of the electromagnetic field, real and measurable, but not a miniature container full of hidden hardware. The moment we stop looking for gears within it, the subject becomes more interesting, because then we can turn to the next question, which is not what a photon contains, but how one begins. Once we stop trying to pry open a photon like a tiny object with hidden compartments, the next natural question becomes much more satisfying. If it is not something assembled from smaller visible pieces, then how does it begin? What does it mean for a photon to come into existence at all? That question brings us to one of the loveliest habits in physics, which is to stop asking what things are made of for a moment and start asking what events create them, because a photon, unlike a pebble or a spoon or a sock that has somehow vanished in the wash, is not the sort of thing that waits on a shelf for later use. A photon is born in a process. It appears when energy changes hands in a very particular way. That already sounds a little abstract, so let us bring it closer to the kind of world we actually live in. Imagine a lamp turning on in a dark room. The switch clicks, the bulb glows, and almost instantly the room is full of visible light. It feels immediate, simple, and perhaps not especially philosophical. Yet hidden inside that ordinary event are countless photons being produced. Or think of a candle flame, or a star, or the red glow of a toaster, or the green exit sign in a hallway, or the little pulse of light inside a remote control. In all of these cases, photons are being born, though not all in the same way. The source matters, the mechanism matters, the energy involved matters, but the broad theme is the same. A photon comes into being when energy that had been stored, transferred or rearranged in some other form is emitted as light. One reason this is worth sitting with is that it tells us something important about the universe. Light is not usually a permanent substance hidden in matter, like jam in a cupboard, waiting to be taken out with a spoon. Matter does not simply contain finished photons in storage. Rather, photons are produced when physical systems change. That change may be an atom dropping from one energy state to another. It may be electric charges being accelerated. It may be particles annihilating one another. It may be thermal agitation in hot matter. It may be nuclear reactions deep inside a star. Different births, different settings, same broad family. Energy is reorganized, and one of the ways the universe allows that reorganization to express itself is through the creation of photons. Let us begin with atoms, because atoms are perhaps the most elegant place to watch the story. An atom is not a little solar system in the old textbook sense, but it does have electrons associated with allowed energy levels. That phrase allowed energy levels is important. Electrons in atoms are not free to have just any energy they like, the way a child in a field may run to any patch of grass. They are constrained by quantum rules. They can occupy certain states and not others. If an electron is given extra energy, perhaps through a collision or through absorbing light, it can move into a higher energy state. It does not stay there forever. Higher energy states are often less stable, rather like someone balancing on a narrow stool when a perfectly good chair is nearby. Sooner or later, the electron may move to a lower energy state. When it does, the difference in energy has to go somewhere. Very often it leaves as a photon. This is one of the cleanest ways to picture a photon being born. Not assembled from parts, not squeezed out like toothpaste, but emitted as a consequence of a quantum transition. The atom changes state, and the energy difference emerges as light. The particular energy of the photon depends on the gap between the two states. A larger gap means a more energetic photon. A smaller gap means a less energetic one. And because different atoms have different allowed states, they produce characteristic patterns of light. This is why heated gases and glowing elements can be identified by the specific colours and spectral lines they emit. Every atom, in a sense, has its own habits when it comes to letting light go. There is something pleasingly economical about that. The photon is not added as an afterthought. It is how the change is expressed. Nature is not holding a meeting, debating whether the energy should be put into a bag and labelled for later. The emission is part of the process itself. An excited system relaxes and a photon is born. If that sounds tidy, do not worry. The universe still has room for variation. Atoms are only one setting. Charges that accelerate can also produce photons. This is important because it widens the idea of light far beyond glowing atoms in isolation. Whenever an electric charge changes its motion, the electromagnetic field responds. Under the right conditions, that changing field can radiate energy away, and the quantum language for that radiated energy involves photons. This is why antennas can emit radio waves. Electrons in the antenna are driven back and forth by oscillating currents. Their motion changes. The electromagnetic disturbance spreads outward, and in quantum terms we describe the radiation in photons appropriate to that part of the spectrum. That is worth pausing over, because it reminds us that visible light is only a small patch in a much larger electromagnetic family. A photon of radio light, A photon of microwave radiation, a photon of infrared, visible, ultraviolet, or gamma radiation are all photons. They differ in energy and frequency, but not in being members of the same fundamental category. When your wireless devices send signals, when a microwave oven heats food, when the sun warms your skin, when an X-ray image is taken, photons are involved in all of it. The universe does not draw hard emotional lines between these kinds of light. Humans do, mostly because some of them we can see and others we cannot. Still, visible light keeps its charm because it is the part woven most directly into ordinary experience. Consider the old-fashioned incandescent bulb, the sort that gets too hot and makes modern engineers sigh with mixed admiration and disappointment. Inside such a bulb, an electric current passes through a thin filament. The filament resists the current and becomes extremely hot. Its atoms and electrons jostle violently. In that thermal agitation, the charged constituents accelerate and interact in ways that lead to the emission of photons across a broad range of energies. Many of those photons are in the infrared, which is why the bulb wastes so much energy as heat, but some are visible, which is why the room glows. Here, the birth of photons is tied not to one neat atomic jump alone, but to the broader behaviour of hot matter radiating because its charged components are in restless motion. A candle works differently in detail but tells a related story. In the flame, chemical reactions break old molecular bonds and form new ones. Atoms and molecules are excited, hot particles collide, soot particles glow, and photons are emitted through several overlapping processes. That familiar warm flicker on a wall, which feels so simple and ancient, is actually a crowded little theatre of photon births. Some arise from specific excited atoms and molecules. Some come from hot glowing particles. The eye sees a smooth flame. Physics sees an ongoing negotiation of energy producing streams of light. Stars, of course, take the whole business to grander levels. The light from the sun does not come from one mechanism alone, but its ultimate source lies in nuclear reactions deep in the core. There, hydrogen nuclei are fused into helium under immense temperature and pressure. In the process, energy is released. That energy does not leap straight from the core to your window in one heroic photon, with a perfect sense of direction. The trip is far messier. Energy produced in the core is repeatedly absorbed and re-emitted, scattered, redirected and transformed through countless interactions in the dense stellar interior. Photons are born, absorbed, replaced, and born again. By the time sunlight escapes the outer layers of the sun and heads into space, it has been through an extraordinarily long chain of events. The photon that finally arrives at your eye is not a little messenger that travelled untouched from the centre. It is part of a continual process by which energy worked its way outward until it could leave the star as radiation. That point is especially important because it helps us avoid another intuitive trap. We often speak as though photons are tiny couriers preserving a simple identity from creation to arrival. Sometimes that is a good enough shorthand, but in matter dense enough, photons do not simply glide untouched through all circumstances. They can be absorbed and new photons emitted. They can scatter. They can be converted into other forms and back again depending on the processes involved. The story is not always one of a single heroic traveller. Often it is a chain of births and endings stitched together by conservation laws and interactions. There is a more dramatic birth route as well, one that would probably have sounded outrageous before modern physics. Matter and antimatter can annihilate and produce photons. If an electron meets its antimatter counterpart, the positron, they can disappear as particles of matter and antimatter and produce photons instead. Not fade politely, not partially dissolve. Completely convert their mass and motion into new products consistent with the laws of nature. In this case, photons are born from the annihilation event. It is one of the clearest reminders that in physics, matter and radiation are not entirely separate kingdoms. Under the right conditions, one can become the other. That sort of process can sound almost mythological if one is tired enough. Two particles meet, vanish, and light appears. But it is not myth. It is part of the ordinary logic of modern physics. Energy and momentum must be conserved. Quantum rules must be obeyed. When the conditions are right, photons emerge. There is no tiny workshop in which they are pre-manufactured. The event itself brings them into being. Another route worth noticing is the one used in lasers, because lasers are often imagined as mysterious high-tech beams when in fact, their core principle is beautifully specific. In a laser, atoms or other quantum systems are prepared in excited states. When one of these systems drops to a lower energy state, it can emit a photon. Under the right conditions, an incoming photon can stimulate that emission, so that the new photon matches the original in direction, phase, and energy. This process can cascade, creating a highly organized beam of light. Lasers do not create a new kind of photon. A photon is still a photon. But the way photons are born inside a laser is unusually coordinated. The emissions reinforce one another instead of arriving in the more random jumble typical of many ordinary light sources. There is something almost social about that. In a hot filament bulb, photon production is busy and unruly, full of many different energies and directions. In a laser, the births are choreographed with remarkable discipline. The result is not merely bright light, but light with a special degree of coherence. The photons are not chatting independently at a crowded market. They are marching with improbable agreement. All of these examples reveal a common idea. A photon is born when a system capable of carrying or rearranging energy changes in such a way that electromagnetic radiation is emitted in quantized form. That sentence is a little stiff around the knees, but it contains the essence. Photons are not hidden inventory. They are events of release, products of transition, expressions of change. This is one reason light is so tied to dynamism. To ask where photons come from is often to ask what is changing. Is an atom relaxing? Is a charge accelerating? Is matter heating? Is matter and antimatter annihilating? Is a molecule changing vibrational state? Is plasma swirling in a star? Is a semiconductor in a device allowing electrons and holes to recombine? In each case, photon birth is the visible or measurable sign that a physical system has moved from one configuration to another. Semiconductors offer a particularly modern and useful example. In devices such as light-emitting diodes, electrons and the absence of electrons, which physicists call holes, can recombine in a material. When that happens, energy is released, often as photons. The properties of the semiconductor determine the energies involved, and therefore the colour of the emitted light. So the little indicator light on a charger or appliance may look modest enough, but it is a quantum device in which the architecture of the material helps determine what kind of photons are born. The universe is doing precise bookkeeping, even in the most ordinary corners of the house. There is also the matter of probability, because quantum processes are not always like clockwork in the way a pendulum is. An excited atom may have a characteristic lifetime before emission becomes likely, but the exact moment a specific photon is emitted can be fundamentally probabilistic. That can unsettle the part of the mind that wants a tiny push at a tiny instant from a tiny hidden cause. Yet nature appears perfectly content with this. We can predict rates and distributions with extraordinary precision, even when individual events retain a degree of inherent unpredictability. So a photon can be born not because a tiny internal alarm clock finally rings at an exact pre-scheduled moment, but because the system has a certain probability of making that transition, and at some point it does. That is one of those ideas that sounds stranger the more everyday examples we compare it with. A kettle boils when enough energy has gone in. A door opens when someone turns the handle. A bus, in a perfect world, arrives when the timetable says it should. But at the quantum level, emission is not always pinned to a definite hidden microschedule. There are stable patterns and lifetimes and probabilities, but not necessarily a tiny determined clock behind every individual photon birth. Physics here is not less precise. It is precise in a different language. Another subtle point is that the birth of a photon is not necessarily a tiny flash confined to a single spot in the naive visual sense. The processes are described through interactions and field transitions, and the emitted state may later be detected in a localized event. One must be careful not to imagine a photon popping out like a bead from a machine slot. The mental image can be useful at times, but only if held lightly. Quantum theory is constantly asking us to use imagery without becoming enslaved to it. Still, for all that caution, the central reality remains wonderfully concrete in experiment. Photons can be counted. Single photon sources can be built. Detectors can register one-at-a-time arrivals. Atomic transitions can be measured. Spectra can be studied. Lasers can be tuned. The births may defy everyday intuition, but they are not beyond science. In fact, modern technology depends on controlling them with astonishing finesse. We build cameras, communication systems, medical devices, sensors, and quantum experiments around the reliable creation and detection of photons. That is part of what makes the topic so charming. Something this strange is also completely practical. It is also worth noticing that a photon is born with properties set by the process that made it. Its energy is not chosen later, like a shirt from a wardrobe. The emission process determines what sort of photon it is in terms of energy, and often influences direction, polarization, and coherence as well. A photon from a thermal source differs in statistical character from one produced in a laser. A photon emitted in a particular atomic transition carries the signature of that transition. A gamma ray born in a nuclear process is not merely a visible photon that went to finishing school and came back with attitude. It reflects the energy scale of the event that produced it. So the birth story already begins to answer questions that at first seem separate. Why do different sources emit different kinds of light? Because different physical changes give birth to photons with different energies and patterns. Why can we use light to learn about distant stars or materials in a laboratory? Because the photons born there carry information about the processes that created them. The birth marks the child, as it were, though perhaps in a more rigorous and less sentimental fashion than that phrase usually suggests. And there is one more comforting thought in all this. The world around us is full of photons being born all the time without ceremony. Warm objects around you are radiating. Electronic displays are emitting. Chemical reactions produce light in some cases. The sky glows by scattered sunlight. Distant stars are constantly generating new radiation. Even in darkness, the universe is not inactive. It is simply sending you fewer of the photons your eyes are tuned to detect. Light is not an exotic exception. It is one of the routine ways the cosmos moves energy around. So when we ask how a photon is born, the answer is not that it is built piece by piece or revealed from a hidden stockpile. A photon is born when a physical system changes and releases energy in the form of electromagnetic radiation, quantized in the way nature requires. Sometimes that happens in an atom relaxing, sometimes in a charge accelerating, sometimes in hot matter glowing, sometimes in annihilation, in lasers, in semiconductors, in stars. Different settings, same fundamental principle. The birth of a photon is an act of transition, and that leaves us in a rather satisfying place, because now the question broadens naturally. If a photon is born from a change in energy, what exactly is it that has been born? What does it mean to say that light comes in quanta at all? We have moved from asking for anatomy to asking for identity, which is usually where physics becomes most interesting. By this point, the question has shifted into a much better shape. We are no longer trying to imagine a photon as a tiny object with a hidden interior, and we are no longer asking only where it comes from. We are now standing in front of a deeper and more useful idea. What does it actually mean to say that a photon is a quantum of light? At first glance, the phrase sounds like the sort of thing science says when it wants to sound impressive in a room with polished floors, quantum of light. It has a certain formal weight to it, but the idea itself is not there to intimidate anyone. It is there because nature turned out to be more particular than people expected. For a very long time, many scientists imagined light as a wave and only a wave. That made excellent sense. Light interferes with itself. It spreads. It bends around edges. It produces patterns that look exactly like what one expects from wave behavior. If you pass light through narrow openings, or send it through certain carefully arranged experiments, it behaves with a kind of elegance that waves are very good at explaining. In that older picture, light seemed like a smooth, continuous thing, something that could in principle be divided and divided again without limit, the way water poured from a jug can be divided into smaller and smaller cups. Then the universe, never shy about rearranging our confidence, began showing that this smooth picture was not the whole story. To say that light is quantized means that when it interacts with matter, it does not always behave like an endlessly divisible fluid. It exchanges energy in discrete amounts, not any amount whatsoever, not whatever fraction happens to be convenient that afternoon. Specific packets. Those packets are photons. A photon is not just a bit of light in the casual sense. It is the smallest indivisible unit in which a particular light field can give or take energy in an interaction. That phrase smallest indivisible unit needs a little care, because it can be misunderstood in two directions at once. On one hand, it does not mean light is made of tiny glowing bricks in the same way a wall is made of physical blocks. On the other hand, it does not mean the quantization is optional or merely a trick of bookkeeping. The discreteness is real. When a single atom emits light in a certain transition, it does not release half a photon now and half a photon after lunch. The exchange happens in a definite quantum event. Likewise, when a detector registers a single photon, it is not receiving a smear of energy spread out continuously through time in the classical wave sense. It is receiving a discrete amount tied to that photon. The importance of this is hard to overstate, because it changes what light is allowed to do. In a purely classical wave picture, one might imagine light energy spread continuously so that very dim light would simply deliver very tiny amounts of energy to matter. That seems harmless until experiments begin objecting. Certain effects, especially at the atomic scale, only make sense if light arrives in definite packets. A famous example is the photoelectric effect, where light shining on a material can knock electrons free. What matters is not merely the total brightness in a vague continuous sense, but the energy carried by each individual quantum. A bright source of lower energy light cannot always do the job, while a dim source of higher energy light can. That was one of the clues that forced physics to take the quantum nature of light seriously. It is worth lingering over that, because it shows the difference between more light and more energetic light. In ordinary language, we often treat brightness as if it were the main feature, and for many daily purposes that is fine. A brighter lamp helps you find your keys. A dimmer room makes the cat look philosophical. But at the quantum level, brightness and photon energy are not the same thing. A very bright beam can be made of huge numbers of relatively low energy photons. A dim beam can consist of fewer photons, each carrying more energy. This is one of the reasons the phrase quantum of light matters so much. It reminds us that light is not just a smooth glow. It is built into interactions one photon at a time, and the character of those photons matters. Historically, this idea arrived in stages, which feels appropriate for a subject that is about discrete steps. Max Planck, while studying thermal radiation, found that the mathematics made sense only if energy exchange came in discrete amounts. He did not begin by announcing that light itself was fundamentally particulate in the modern sense. He was trying to make sense of how hot objects radiate. Then Albert Einstein took the idea further and treated light as consisting of energy quanta in order to explain effects that a purely continuous wave picture could not handle. In time, experiment after experiment gave support to the quantum description. Light remained wave-like in many respects, but it also insisted on behaving as though its energy came in these definite packets. This is where people often become understandably suspicious and ask whether physics is cheating by giving light two personalities whenever convenient. A wave when that helps, a particle when that helps, and everyone else is expected to nod along politely. It can sound like one of those explanations that would not survive 5 minutes in an ordinary conversation, but the point is not that light secretly changes its mind like a moody actor between scenes. The point is that the classical categories of wave and particle, which were built from everyday experience, are both too narrow to capture the full reality. A photon is not a tiny billiard ball, yet neither is light merely a continuous wash. The quantum description is deeper than both. Calling a photon a quantum of light is a way of pointing toward that deeper reality. One helpful way to think about it is to remember that the word quantum does not mean mysterious in the vague cinematic sense. It means discrete. It means that some physical quantity comes in specific units rather than in an uninterrupted continuum. Money offers a modest everyday analogy, though not a perfect one. If you owe someone a certain amount, you might pay with coins or notes in definite values. You do not usually peel off an arbitrary fraction of a coin. The system comes in units. Light is not money, and photons are not coins, but the analogy helps with the idea that energy transfer is chunked. The trouble comes only if we push the picture too far and start imagining photons as little hard tokens clattering through space. The quantization is the useful part of the analogy. The tiny object imagery is where it begins to fail. Another way to say it is this. In the classical picture, a wave can in principle be made as weak as you like and still remain fundamentally the same kind of thing. In the quantum picture, if you keep reducing the amount of light in a given mode of the electromagnetic field, you do not get an endlessly thinning soup. You get fewer photons, one photon, then none. That is a profound shift in thinking. It tells us that light is not just weak or strong in the old continuous sense. It is also countable in its basic interactions. This countability has been demonstrated in deeply convincing ways. Experiments can produce and detect single photons. Sensitive detectors can register light one quantum event at a time. When the light is weak enough, you do not get a vague almost event. You get individual detections, little clicks, flashes, registrations depending on the apparatus. This is one of those places where the abstract language suddenly becomes wonderfully concrete. The universe is not merely letting physicists talk poetically about packets. It is letting them build devices that respond to those packets one by one. Yet even here we have to stay careful, because a photon being countable does not mean it travels like a tiny grain in the classical sense. This is one of the hardest balancing acts in the subject. The photon is a quantum, yes, it is countable in interactions, yes. But its behaviour between source and detection is described by quantum theory in ways that still retain wave-like structure. Interference does not disappear simply because the energy arrives discretely. In fact, one of the most astonishing facts in physics is that if you send photons one at a time through an interference setup, the overall pattern that builds up over many events still reflects wave behaviour. Each individual detection is localized, but the statistical pattern carries the signature of interference. So the quantum of light is not a retreat from wave behaviour. It is a refinement of our understanding of what wave behaviour and particle-like detection can mean together. That is why the phrase quantum of light is so valuable. It does not force us to choose the wrong old category. It says instead that the electromagnetic field has quantized excitations, and that these excitations are what we call photons. Now, if one says that too quickly, it can sound as though we have simply replaced one mystery with another more expensive sounding mystery. Field, excitation, photon, all very grand. But the idea is not as forbidding as it appears. Think of a violin string. The string can vibrate. Different vibrations are possible. The vibrations are not separate objects floating above the string, they are states of the string itself. In a loose and very limited analogy, the electromagnetic field is like the underlying entity, and photons are quantized excitations of that field. The analogy breaks down if pushed too far, but it helps with the key idea that a photon is not a little pellet, inserted into a field from outside. It is a quantized state of the field. This also helps explain why all photons of a given type are identical. If photons were tiny hand-built gadgets, one might wonder whether some are slightly crooked or badly assembled on Mondays. But photons are not manufactured items with tiny variations in craftsmanship. They are fundamental quanta. A photon of a given energy and polarization is indistinguishable in its fundamental properties from any other photon with the same relevant quantum features. This sameness is not dull. It is one of the reasons the universe is mathematically tractable at all. If every photon had a private personality disorder, spectroscopy would be a much gloomier profession. It also clarifies why a photon cannot simply be chipped into smaller light pieces of the same kind. If you take a loaf of bread and cut it, you get smaller bread. If you pour water into 2 cups, you get smaller quantities of water. But if you have a single photon of a particular energy, you do not split it into 2 lower energy photons by ordinary division the way one splits matter in daily life. Certain physical processes can transform one photon into multiple photons under appropriate conditions, but that is not the same as slicing it like cake. The original quantum event is replaced by new quantum events consistent with the laws of conservation and interaction. The language of chopping and carving is not the right language. The discreteness of photons also changes how we think about emptiness. In everyday life, a dark room feels empty of light in a simple way. But quantum physics teaches a more nuanced lesson. The electromagnetic field is a real part of physical reality, and photons are excitations of it. Darkness, then, does not mean the field has ceased to exist. It means that in the relevant modes and energies there are fewer or no photons reaching you in a way your eyes detect. That may sound subtle, but it matters. The field is not a stage that sometimes vanishes. It is always part of the description. Photons are particular quantum states of that field, not the whole field itself. There is also a deep relationship between the quantum nature of light and the structure of matter. Atoms have discrete energy levels, as we discussed earlier. The fact that light is quantized meshes with that beautifully. An atom absorbing light does not slurp up a continuous drizzle of arbitrary energy until it feels ready to change. It absorbs a photon with the right energy to match an allowed transition, or it does not. The fit matters. There is a selectivity to these processes that would make less sense in a purely continuous world. Matter and light, both governed by quantum rules, meet each other in these discrete transactions. It is as though reality at that scale prefers properly denominated exchanges. This selectivity is why spectroscopy is so powerful. By studying what light is emitted or absorbed, scientists can infer what atoms and molecules are present and what states they occupy. The photons involved are not vague carriers of glow. They are precise signatures of permitted energy differences. That is one more reason the phrase quantum of light is not just philosophical garnish. It is operationally useful. It tells us why light can reveal structure so accurately. The discreteness gives it sharpness. Now, it is very tempting at this point to imagine that the quantum description simply makes everything grainy, as if the world were a digital photograph and photons were pixels. That is not quite right. A pixel is tied to a grid and a fixed representation. A photon is not a little square of light occupying one neat location in a prearranged cosmic screen. Quantum theory is subtler than that. The discreteness concerns the excitation and exchange of energy, but the states themselves can still have complex spatial behavior, interference properties, and probabilistic descriptions. So we should resist the urge to turn quantum light into crude, blocky light. Nature is more elegant than that, and to be honest, more difficult. The elegance becomes even clearer when we consider that the same photon concept applies across the entire electromagnetic spectrum. The gentle radio photon and the punishing gamma photon are both quanta of the same field, differing in energy and frequency. Visible light is just the narrow middle region that our eyes happen to evolve to notice. That accident of biology can make us forget how broad the family is. A photon is not defined by visibility. It is defined by being the quantum of electromagnetic radiation. The universe is full of photons we never see directly, just as it is full of sounds no human ear can hear. Our senses are not the standard by which reality organises itself. There is a philosophical temptation here as well, though I will keep it on a short leash. Once you realise that what feels like smooth light is, in interactions, quantized, you begin to see a broader pattern in modern physics. Many things that appear continuous at human scales reveal discrete structure when examined more deeply. Matter, charge, atomic energy levels, and now light all participate in this layered reality where ordinary appearance and fundamental description are not the same. That does not make the visible world false, it makes it emergent. The smoothness we live with is often the large-scale effect of many quantum events blending into something the human brain can handle before breakfast. And yet there is no need to become gloomy or suspicious about common sense. Common sense is not wrong. It is local. It works beautifully within the domain that shaped it. It helps you cross a street, pour tea, and avoid walking into doors. It simply was not designed for photons. The quantum of light is one of those truths that asks us to expand common sense rather than discard it. Once you get used to the idea, it becomes less alarming and more satisfying. Light is neither a classical wave alone nor a little object alone. It is something quantum, and the photon is the name we give to its discrete excitations. There is also something quietly reassuring in the fact that this strange idea is not speculative decoration sitting on the edge of physics. It is woven into the technologies and measurements that define the modern world. Solar cells rely on photons delivering energy to electrons in matter. Digital cameras register photons and convert their effects into electrical signals. Medical imaging, telecommunications, laser systems, optical sensors, quantum experiments, all of them depend on the reality that light comes in quanta. This is not a poetic way of speaking about glow. It is a practical truth with wires and circuits attached. So when we say a photon is a quantum of light, we mean that light is not exchanged with matter in an endlessly divisible classical flow. It comes in discrete packets of energy that are the fundamental excitations of the electromagnetic field. Those packets can be counted. They carry definite energy and momentum. They participate in interactions one event at a time. Yet they also belong to a deeper framework in which wave-like behavior remains essential. The phrase is compact, but it holds an entire evolution in understanding. And once that idea settles in, another question begins to press gently against the door. If a photon is not a tiny object moving through some material medium the way a boat moves through water, then what does it mean for light to travel as a wave at all, especially through empty space? That is where the story becomes even more interesting, because the moment you understand that light is a quantum, you also have to ask what it is waving in the first place. Now we come to one of the most surprising features of light, and it is surprising partly because our instincts are trained on the wrong examples. When most of us hear the word wave, we think of something moving through something else. Ocean waves move through water. Sound waves move through air. Ripples move across a pond. A stadium wave moves through a crowd that, for reasons known only to the crowd, has agreed to cooperate. In every familiar case, the wave seems to need a material medium. There has to be some substance doing the actual waving. Water rises and falls. Air compresses and expands, people stand up and sit down. So when physics tells us that light is wave-like, the natural response is to ask a very reasonable question: what is waving? For a long time, scientists asked exactly that. It did not seem possible that light could be a wave without a medium, because waves were understood through the examples available to human senses and daily life. If sound needed air and water waves needed water, surely light needed something too. Since light clearly travels across what appears to be empty space from the sun to the earth, the proposed answer was that space was not truly empty after all. It must be filled with some invisible substance, an all-pervading medium through which light could travel. This hypothetical substance became known as the ether. The ether was meant to be extremely accommodating. It had to fill all space because light from the stars reaches us from every direction. It had to be transparent because we do not notice it directly. It had to be delicate enough not to slow planets and comets in any obvious way, yet sturdy enough to support tremendously fast light waves. In hindsight, this is the sort of arrangement that should make one slightly nervous. Whenever a theory requires a substance with an increasingly specialized personality, there is a chance the universe is trying to tell you that the whole category is wrong. Still, the ether idea was not foolish. It was an honest attempt to preserve the familiar logic of waves. If something waves, something must be there to wave. The problem was that as experiments improved, the ether became harder to defend. Scientists tried to detect the motion of the Earth through this supposed medium, rather as one might feel wind while moving through still air. If Earth was travelling through an ether that filled space, then the speed of a light measured in different directions ought to reveal some trace of that motion. The most famous attempt to detect this effect came from the Michelson and Morley experiment in the late 19th century. The result was famously awkward for the ether. No such effect appeared in the expected way. The experiment did not behave like a simple detective story in which the suspect immediately confesses, but it certainly made the ether look increasingly unhelpful. This is where the subject becomes especially interesting, because the solution was not that light had secretly stopped being wave-like. The solution was that the need for a mechanical medium was an assumption borrowed from the wrong kind of wave. Light is not like sound in that sense. Sound is a disturbance in matter. Air molecules nudge neighbouring molecules, and the pressure pattern travels. If there is no matter, there is no sound. That is why outer space is silent in the ordinary acoustic sense. No air, no compression wave, no dramatic explosion noise, however much films may enjoy pretending otherwise. Light is different. Light does not need matter in order to propagate. It is a disturbance of the electromagnetic field itself. That phrase electromagnetic field can sound like the sort of thing that gets announced in a lecture hall while half the audience quietly hopes for a biscuit. But it is really the key to the whole business. A field in physics is a way of describing how a physical quantity exists throughout space. Gravity can be described as a field, electric influence can be described as a field, magnetic influence can be described as a field. These are not fluids sloshing about in the everyday sense. They are ways reality is structured. If you place an electric charge somewhere, it changes the electric field around it. If charges move, magnetic effects appear as well. Over the 19th century, physicists, most notably James Clerk Maxwell, discovered that electricity and magnetism are not separate stories awkwardly sharing a hallway. They are aspects of one unified electromagnetic structure. Maxwell found that changing electric fields can produce magnetic fields, and changing magnetic fields can produce electric fields. That simple-sounding statement has enormous consequences. It means that under the right conditions, a self-propagating disturbance can travel through space. A changing electric field gives rise to a changing magnetic field. That changing magnetic field, in turn, gives rise to a changing electric field. The pattern sustains itself and moves outward. There is no need for air or water or some hidden jelly spread across the cosmos. The electromagnetic field is the thing that is changing. Light is that travelling disturbance. This takes a bit of getting used to because it asks us to promote the field from a bookkeeping convenience to a real physical entity. If one keeps thinking of fields as merely a way of talking about forces between objects, then the whole idea feels slippery. But modern physics treats fields as fundamental parts of the world. They are not decorative language layered on top of more real machinery. They are the machinery, or as close to machinery as the universe seems willing to provide in this case. So asking what medium light moves through turns out to be a little like asking what medium gravity moves through when the Earth orbits the Sun. The question assumes the wrong kind of setup. Not every physical effect is a wobble in material stuff. This is one of the moments where our daily experience begins to lose its authority. The brain says a wave needs a medium because every wave I have met so far has had one. physics replies that every wave you have met so far has been a human-scale mechanical wave, and human-scale mechanical waves do not get to set policy for the entire universe. That is fair enough, though one does sometimes feel the universe could be a touch gentler when correcting us. The beauty of Maxwell's picture is that it not only freed light from the need for a medium, it also explained something else remarkable. The speed that emerged from the electromagnetic constants in his theory matched the known speed of light. That was a stunning clue that visible light is electromagnetic radiation, not a separate mysterious substance, not a divine special case, part of the same broader family as radio waves and all the rest. Once this fell into place, the idea of riding a wave without a material medium stopped looking like a paradox and started looking like a clue that fields are more fundamental than matter in this domain. Still, one must be careful not to picture the electromagnetic field as a kind of hidden gas filling the universe, because that simply sneaks the medium back in through a side door. A field is not a material background in the everyday sense. It does not consist of tiny particles standing shoulder to shoulder, waiting for light to pass along gossip. It is a physical structure that can exist in vacuum. The vacuum in modern physics is not a crude nothing. It is the state in which there are no particles present in a certain sense, yet the field still exists as part of reality. So when light crosses empty space, it is not cheating. Empty space, in the old naive sense of absolute blankness, was never the full story. This matters especially when we connect it back to photons. In the classical theory, light can be described as an electromagnetic wave. In the quantum theory, photons are the quanta of that electromagnetic field. These are not rival accounts in the way one rival football club resents another. They are connected levels of description. The wave language captures the field behaviour beautifully in many contexts. The photon language captures the discrete quantum interactions. So when we talk about a photon riding the wave without a medium, we are really dealing with a quantum excitation of a field that propagates through vacuum according to the structure of that field. No ocean required, no ether required, no microscopic invisible marbles to push it along. There's another helpful comparison here. A sound wave tells you that matter is being disturbed. Light tells you that the electromagnetic field is disturbed. That is why sound cannot cross interplanetary space, but sunlight can. The heat you feel from the sun is not the result of warm air travelling from the solar surface through the void, which would be an alarming bit of weather if true. It is electromagnetic radiation carrying energy across space. The vacuum between the sun and Earth does not smother the wave because the wave is not a compression of matter. It is an electromagnetic disturbance. At this point, people often ask whether the field itself counts as a medium after all, just under a more respectable name. The answer depends on how strictly one uses the word medium. If by medium you mean any physical thing in which some phenomenon exists, then one might say the field is the relevant underlying entity. But if by medium you mean a material substance like air or water, whose particles jiggle and transmit the wave mechanically, then no, the field is not a medium of that sort. The distinction matters because the old ether picture imagined something more like a hidden material framework. The modern field picture does not require that. One of the reasons this is hard to internalise is that we like to imagine transport in terms of little bits handing things to neighbouring bits. Water waves are easy because you can imagine each bit of water nudging the next. Sound is easy because each air molecule bumps nearby molecules. Light asks us to step away from that picture. The propagation is built into the coupled structure of the electric and magnetic fields. The mathematics of the theory describes how the disturbance evolves and moves. There is no line of tiny couriers passing a folded note from one end of the universe to the other, and yet despite all this talk of fields, light still behaves with tremendous concreteness. A beam can be reflected by a mirror, focused by a lens, absorbed by a detector, scattered by molecules in the atmosphere. If it were only an airy theoretical fiction, it would not be nearly so useful. The electromagnetic field is not some philosophical convenience. It has consequences you can measure, build with and rely upon. Radio communication, optical fiber, solar energy, remote sensing, wireless technologies, imaging systems, all of these depend on the fact that electromagnetic disturbances propagate through space without a material carrier. If light needed air, astronomy would be a far sadder profession. There is also a subtle but important change in perspective here. In everyday life, matter tends to feel primary and fields feel secondary, as if the solid things are the real cast and the fields are just the lighting and stage directions. Modern physics often nudges us toward a different view. Fields are not merely added effects surrounding objects, they are part of the deep description. Particles, including photons, are understood in terms of field excitations. Once that point settles in, the question of what medium light needs begins to look a bit like asking what paper the weather needs to exist on. The description was borrowing too heavily from the wrong analogy all along. Of course, there is still the very practical matter of how one is supposed to picture a wave if there is nothing visibly sloshing up and down. Textbooks often show electric and magnetic fields oscillating at right angles to each other and to the direction of travel. That picture is useful, but it can be misleading if taken too literally as a little vibrating ribbon moving through space like a festive but disciplined snake. The oscillation refers to the changing values and orientations of the fields, not to a chunk of stuff physically bobbing up and down in a background medium. The diagram is a map of behaviour, not a photograph of hidden furniture. This is the same caution we have been needing all along. Classical pictures can guide us, but only if held lightly. Treat them too literally, and they begin smuggling in assumptions that quantum and field theory no longer support. A photon is not a tiny glowing bead. An electromagnetic wave is not a wobble in cosmic pudding. Vacuum is not simple nothingness. Each time the mind reaches for a familiar image, physics says yes, that may help at first, but do keep your coat on because we are not stopping there. There is another reason the wave without a medium matters. It tells us something profound about the universality of the electromagnetic field. The same kind of entity that fills your room with visible light also carries radio broadcasts across cities and starlight across galaxies. The medium is not local. There is no special substance around the Earth that light needs, and then abandons when it gets ambitious. The field is a basic part of space-time itself, as we currently describe the world. That is why light from a distant galaxy can cross unimaginable emptiness and still arrive with usable information. The wave has not been clinging to secret matter all along. The possibility of propagation is built into the field structure of reality. And here is where the story begins to fold back into the photon again. When we say a photon is a quantum of the electromagnetic field, we are not speaking metaphorically. The field is the underlying reality whose excitations behave in the ways we call light. The wave description tells us how disturbances of the field propagate. The quantum description tells us that the energy of these disturbances is exchanged in discrete amounts. So riding the wave without a medium does not mean a tiny object surfing on an invisible ocean. It means that the propagation of electromagnetic structure through vacuum is the background story in which photon behaviour makes sense. There is a curious comfort in that once one gets over the initial insult to common sense. The universe is not requiring hidden substances just to patch our intuitions. It is offering a cleaner rule. Light does not need a material carrier because the electromagnetic field is itself capable of supporting propagating disturbances. That is simpler, even if it takes longer to feel simple. It is often like that in physics. The deeper truth looks strange at first because the familiar picture had been doing too much work. And because this wave is not the same kind as a water wave or sound wave, it comes with properties of its own that deserve closer attention. The way the field oscillates is not random. The directionality matters. The orientation matters. Those features turn out to be part of what gives light its polarization. And once that enters the story, the photon begins to reveal more of its character than the old particle image ever could. If the last idea left us with light travelling as a wave through empty space, the next question arrives almost on its own. If this travelling disturbance has no little engine inside it, and no material medium around it doing the heavy lifting, then what sort of character does it have? What distinguishes one photon from another besides energy alone? Because by now it should be clear that a photon is not featureless. It may not have an inside in the ordinary sense, but it does have properties, and some of the most revealing ones are tied to spin and polarization. These are words that often sound more intimidating than they need to. Spin sounds as if the photon ought to be twirling like a cricket ball or a very determined top. Polarization sounds like it belongs in a conversation about sunglasses, camera filters, or an uncomfortable family dinner. In physics, though, both ideas tell us something deep and very specific about light. They are part of the hidden character of the photon, not hidden because physics cannot study them, but hidden because they are not obvious from casual experience. You can live a long and reasonably respectable life under sunlight and lamplight without ever needing to think about polarization at all. The light keeps doing its job. Your eyes remain blissfully unconcerned. Yet the moment you start asking what a photon is really like, these properties become impossible to ignore. Let us start with polarization, because it is easier to observe directly, even if the deeper explanation takes a little patience. In the classical wave picture of light, the electromagnetic disturbance has an orientation. The electric field and magnetic field are oscillating as the wave moves along, and the direction of that oscillation matters. If the electric part of the wave is oscillating in one particular plane, then the light is said to be polarized in that way. This is not just a decorative technical detail. It affects how light interacts with materials. It affects glare. It affects reflection. It affects certain kinds of crystals and optical devices. It even affects how some animals navigate and how many instruments gather information from the world. A very ordinary encounter with polarization happens when light reflects from a flat surface such as water, glass, or a wet road. The reflected light can become partially polarized. That is why polarized sunglasses are so effective at reducing glare. They are not dimming the world in a random way. They are filtering light according to its polarization, blocking much of the reflected light that has a particular orientation while allowing other light through. It is one of those quietly satisfying examples of advanced physics living inside a completely ordinary object. You put on a pair of sunglasses at a bright lake, and without thinking about it, you begin participating in a story about electromagnetic field orientation and photon properties. In the quantum picture, polarization is carried by the photon. This is where the language becomes especially interesting, because it shows how the classical and quantum accounts fit together rather than compete. A classical beam of polarized light corresponds in quantum terms to photons prepared in a certain polarization state. The wave picture tells you about the orientation of the electromagnetic disturbance. The quantum picture tells you that individual photons have corresponding polarization properties that influence how they behave in interaction. The two descriptions are not enemies. They are two levels of the same reality speaking in different accents. Now comes spin, which is related but slightly more subtle. In quantum physics, spin is an intrinsic form of angular momentum. That is the official phrase, and it sounds like it arrived wearing a tie. But the key word there is intrinsic. A photon has spin not because it is literally a tiny object spinning around an axis the way a coin spins on a table. If you picture that too literally, trouble begins almost immediately. A classical rotating object has a surface, an extent, and a mechanical motion through space. A photon, as we have already seen, is not built like that. It is not a miniature ball with painted stripes whirling furiously as it travels. Spin in quantum physics is not that sort of rotation. It is a fundamental property, part of the identity of the particle, as basic as charge is for the electron. This is one of those moments where language betrays history. Early physicists needed names for newly discovered properties, and they chose words borrowed from the world of ordinary rotation because there were similarities in the mathematics and in the way angular momentum behaved. That was useful, but it also left generations of students imagining tiny particles spinning like microscopic planets. The mathematics was onto something real, The imagery was only partially helpful. A photon has spin, yes, but not the kind that would make sense if you tried to photograph it as a rotating bead. The better way to think of it is as an intrinsic quantum property connected to angular momentum and to the allowed polarization states of light. For photons, the spin value is 1. That sounds neat and tidy until another complication politely enters the room. If you are thinking in terms of ordinary spatial directions, you might expect a spin 1 particle to have 3 possible spin orientations along a chosen axis. That is what happens for some other particles. But the photon is massless, and massless particles are special in ways that keep ambushing intuition. A photon does not have all the same freedom of orientation that a massive spinning object would have. In practice, the physically realized spin states of a photon correspond to 2 possibilities, often described in terms of helicity, which means the projection of spin along the direction of motion. Very loosely, one may think of these as two-handedness options for how the electromagnetic disturbance is oriented as it propagates. The photon can have one helicity or the other, but not a third stationary kind in the direction of travel. That probably sounds a little abrupt, so let us unpack it more gently. Imagine light travelling forward. The electromagnetic field associated with it is transverse, which means the oscillations are oriented perpendicular to the direction of motion. They are not sloshing forward and backward along the line of travel like a compressed spring. Because of that transverse nature, the physically meaningful polarization states are tied to sideways orientations. If the field oscillates in one fixed plane, that corresponds to linear polarization. But linear polarization can itself be understood as a combination of 2 more basic circular polarization states, one corresponding to one helicity and the other to the opposite helicity. In that deeper sense, the 2 fundamental spin-related states of the photon are connected to 2 possible handed circular patterns. There is something slightly delightful about that. The hidden character of the photon is not hiding gears or secret compartments. It is hiding sophistication. What looks like a straightforward beam from a lamp or a star carries an internal quantum structure of possibilities. It can be linearly polarized, circularly polarized, or elliptically polarized depending on how the field orientation behaves, and these possibilities are rooted in the spin structure of the photon itself. Light, in other words, is not merely a stream of identical blank messengers. It has orientation, handedness, and angular momentum content. This matters physically. Polarization determines how light interacts with materials. Some molecules absorb one polarization more readily than another. Some crystals can split light according to polarization. Optical instruments use polarization to control transmission, reduce glare, analyze stress in transparent materials, and encode information. In laboratories, polarization is one of the most important handles scientists use when preparing and measuring photon states. It is not ornamental. It is operational. The hidden character of the photon becomes visible in effects that can be built into devices, experiments, and technologies. There is also an elegance in the way polarization bridges the classical and quantum worlds. A classical electromagnetic wave can be drawn with a certain polarization pattern. A single photon can be prepared in a polarization state. Many photons together can form beams whose polarization properties match the classical wave description. That continuity is one of the things that makes quantum physics feel less like a replacement of older physics, and more like a deeper layer that explains why the older descriptions work so well when large numbers are involved. A beam of polarized light is not a separate phenomenon from polarized photons. It is the large-scale expression of those photon states collected into a coherent or partially ordered whole. Still, there is a subtle and very quantum aspect to this story that deserves care. A photon does not always have a polarization that is simply waiting there to be read off like a shirt colour in a wardrobe. In quantum mechanics, states can be superpositions. A photon can be prepared in a state that does not correspond to one definite linear polarization with respect to every possible measurement basis. How it behaves depends on how you ask the question. That is a dangerous sentence because it can sound as though the photon is indecisive or nature is improvising, neither of which is quite right. The point is that quantum properties are not always like classical labels pinned to an object independent of measurement context. A photon prepared in one polarization basis may show probabilistic results when measured in another. This is not sloppiness in the theory. It is one of the basic features of quantum structure. Polarizing filters provide a simple doorway into this weirdness. If light passes through a filter aligned in one direction, only the part of the light matching that polarization is transmitted. Rotate a second filter relative to the first, and the transmitted intensity changes. Turn it the wrong way and the light can be nearly extinguished. This is already interesting enough in the classical picture. But with very low intensity light, the same logic can be understood photon by photon. A given photon encounters the filter, and the probability of transmission depends on the relation between its polarization state and the filter orientation. The outcome for any one photon is discrete. It either passes or it does not. But the probabilities line up with the same mathematical structure that describes the classical intensity change for large numbers of photons. Again, the two descriptions are not rivals, they are layered views of one underlying behavior. The spin of the photon also means that light can carry angular momentum. That phrase may sound like it belongs in a machinery workshop, but it has real and sometimes surprising consequences. Light can exert torque on small objects. Carefully structured beams can transfer angular momentum to particles, making them rotate. This is not science fiction, or a bar bet gone too far. It is part of how light interacts with matter when its angular momentum content becomes relevant. The fact that something with no rest mass and no ordinary inside can still carry angular momentum is one of those facts that would have sounded unreasonable, if not for the very stubborn habit of experiment agreeing with it. There is a temptation here to imagine the photon as secretly more object-like than we have allowed, precisely because angular momentum feels like the sort of thing objects ought to have. One thinks of spinning wheels, rotating dancers, turning planets. But once again, quantum physics asks for discipline. The photon carries angular momentum, yes, but that does not make it a miniature wheel. Fundamental particles have properties that mimic, extend, or generalize classical concepts without collapsing into classical pictures. Spin is one of the best examples. It behaves like angular momentum in the ways that matter for conservation and interaction, but it is not built from literal spinning matter. That distinction is easy to say and annoyingly hard to feel at first. Over time, it becomes less irritating. Another reason the photons' spin and polarization matter is that they reveal a great deal about symmetry in nature. Physics often advances by noticing what can change and what must remain the same. Symmetry principles tell us which transformations leave the laws of physics unchanged. Spin is tightly tied to how particles behave under rotations. Polarization reflects how electromagnetic states transform and interact. So these are not merely descriptive accessories, they are connected to the deep architecture of the theory. If photons did not have the spin structure they do, the behavior of light would be different in ways that would ripple through optics, atomic transitions, and the entire electromagnetic story. This becomes particularly important in quantum communication and information science, where polarization is often used as a way of encoding quantum states. A photon can serve as a carrier of information, not only because it travels well and interacts selectively, but because its polarization states can be prepared, transformed, and measured with exquisite precision. Quantum cryptography, for example, often relies on the fact that measuring polarization in the wrong basis disturbs the state in detectable ways. The hidden character of the photon becomes a practical resource. It is always pleasing when the universe takes a subtle property and allows engineers to turn it into a working technology. There is also a natural connection here to how photons are emitted and absorbed by atoms. The polarization and angular momentum properties of a photon are not random decorations added after birth. They are woven into the emission process itself. When an atom changes state and emits a photon, conservation laws must still be satisfied. Angular momentum must be accounted for. The emitted photon can carry away angular momentum in a way that reflects the transition. Likewise, when matter absorbs a photon, the polarization of that photon can determine whether the interaction is allowed or favoured. So spin and polarization are not things a photon casually acquires on a journey. They are part of the bookkeeping of how light and matter talk to one another. That conversation between light and matter becomes especially rich in materials where polarization effects are pronounced. Some substances are birefringent, meaning they respond differently to different polarizations, splitting an incoming beam into two paths. Some molecules are chiral, meaning they have handedness and interact differently with light of different circular polarization. Entire measurement techniques have been built around these sensitivities. Chemists, physicists, biologists, and engineers all use polarization as a probe because the world does not treat all orientations of light equally. The photon's hidden character turns out to be one of the reasons light is such a fine investigative tool. Perhaps the most useful mental shift in all of this is to stop thinking that a thing must have an inside to have depth. We started with that question long ago, and it keeps echoing in useful ways. A photon has no inside like a toy or a fruit or a battery, but it is not shallow. Its depth is in its properties, in the field structure it belongs to, in the quantum states it can occupy, and in the precise ways it participates in the laws of conservation and symmetry. Spin and polarization are part of that depth. They are not compartments tucked away within it. They are dimensions of what it is. There is a nice philosophical modesty in that. The world is under no obligation to make its foundations resemble the objects that furnish our kitchens. A photon does not need a tiny spinning axle to carry spin. It does not need coloured stripes to possess polarization. It only needs to be the kind of quantum entity that the theory and experiment say it is. Once one accepts that, the subject becomes not only less confusing but more beautiful. The hidden character of the photon is not hidden because it is buried. It is hidden because one must learn the right language to notice it, and that language, once learned, begins to open the next door. Because if a photon can carry energy, momentum, spin, polarization, and angular momentum across empty space while remaining one of the fundamental quanta of the electromagnetic field, then the next thing worth asking is not what more it contains, but how all these properties let it transport energy so effectively from one place to another. Once spin and polarization are on the table, the photon starts to look less like a tiny anonymous packet, and more like a very specific kind of physical event, one that carries a defined amount of energy and momentum while moving through space in a way that no ordinary object quite does. That raises the next question in the most direct possible form. How does a photon actually carry energy across empty space? At first, the answer seems as though it ought to be embarrassingly simple. Light leaves a source, travels outward, reaches something else, and delivers energy there. A lamp warms your hand a little. Sunlight heats a wall. A solar panel produces electrical power. A camera sensor records an image. The process is so familiar that it almost hides itself, yet the moment you stop and look closely, it becomes strange again. Empty space is, at least in the ordinary sense, empty. There are no air molecules lined up all the way from the sun to the earth, carrying little parcels of brightness one after another like a relay team. There is no hidden pipeline running between a star and your skin. There is no visible track laid down ahead of a photon, no glowing wire suspended through the vacuum, and still the energy gets there. This is one of the places where the field picture becomes absolutely essential. A photon carries energy across empty space not by pushing through a material medium but by being a quantum excitation of the electromagnetic field. That field exists in space itself. When we say light propagates, we mean that the electromagnetic disturbance evolves and moves according to the structure of the field and the laws that govern it. In the quantum description, the energy of that disturbance is not a smooth, arbitrary smear. It is quantized. The photon is that quantized carrier. That phrase carrier can be useful, though like all useful words in this subject it becomes dangerous if one leans on it too hard. A carrier in everyday life is often imagined as a little object containing cargo. A truck carries furniture. A ship carries containers. A backpack carries books and bits of old chewing gum. A photon is not like that. It does not have energy packed inside it the way a suitcase contains shirts. The photon is not separate from the energy it carries. The energy is part of what the photon is. To ask where inside the photon the energy sits would be to step back into the same trap we spent so much effort avoiding earlier. The photon is the quantized excitation, and the energy is inseparable from that excitation. That distinction matters because it helps us avoid picturing light as though it were made of tiny glowing beads filled with power like microscopic batteries. Nothing inside a photon stores the energy the way a battery stores charge chemically. The photon's energy is bound up with its state, with its frequency, with the way the electromagnetic field is excited. It is more accurate to say the photon is an energy-carrying event than a little container with energy sloshing around in it. This becomes clearer if we compare light with something like heat moving through a metal spoon. If you place one end of a metal spoon in hot soup, the other end eventually becomes unpleasantly warm. The energy moves through the spoon because particles in the material interact with one another. The internal motion and collisions transfer energy along the solid. That is transport through matter. A photon does something very different. It does not require a chain of neighbouring particles to pass the message along. It crosses empty space because the electromagnetic field itself supports propagation. The photon is a quantum of that propagating field. Perhaps the most vivid example is sunlight. The sun releases a tremendous amount of energy in the form of electromagnetic radiation. Some of that radiation crosses the distance to Earth and arrives at the top of the atmosphere after a journey through space that contains remarkably little matter. That energy then warms land, drives weather, powers photosynthesis, and, if you have been clever with the placement of a solar panel, charges devices that are somehow never charged when you need them. The key point is that the energy did not need a material handhold all the way across. The field structure of reality allowed it to travel. The same idea shows up in every ordinary beam of light. A desk lamp sends photons across the room. They strike a book, a wall, a pair of glasses, the back of your hand. Some are absorbed, some reflected, some scattered. The room becomes visible because energy and momentum are being transferred from the electromagnetic field to matter in countless tiny interactions. The space between source and object does not need to be full of stuff doing the transfer. The photon itself is the transfer mechanism at the quantum level. Now, when people hear that a photon carries energy, they often imagine that the energy must gradually leak out as it goes, the way a thrown ball slows down because of air resistance, or the way a package might get lighter if bits fell off the back. That is a very understandable instinct because most transport in daily life involves losses. Cars waste fuel as heat. Pipes lose pressure. Voices fade with distance because sound spreads and gets absorbed. Light can, of course, be absorbed or scattered by matter if matter is present, but in a vacuum a freely propagating photon does not gradually spend itself just by travelling. It does not become tired. It does not get winded. It does not arrive saying it would have delivered more energy had the route been shorter. If a photon is emitted with a certain energy and travels through empty space without interaction, it retains that energy until an interaction changes the situation. That constancy is one reason light is such an effective messenger across large distances. A photon leaving a distant star can carry information about conditions there all the way to a telescope. Not because the universe has preserved a little sealed message capsule in the everyday sense, but because the photon's properties are stable under propagation through empty space. Of course, there are important caveats in cosmology and relativity, where the expansion of space and relative motion can affect the observed energy. But the broader point still stands. The photon's ability to carry energy through vacuum with extraordinary reliability is one of the reasons astronomy works at all. It is also helpful to distinguish between the energy of individual photons and the intensity of a beam. These are related, but they are not the same. A stronger beam can mean more photons per unit time, or photons of higher energy, or both depending on the source. This matters because energy transport in light is not only about what each photon carries, but also about how many photons are arriving. A dim red light and a bright blue light differ in more than one way. The photons involved may differ in energy, and the total number arriving may differ as well. Your eye or detector responds to the combined effect of all those arrivals, but at the fundamental level the transport still happens one photon interaction at a time. This is where the quantum nature of light becomes especially practical. When a detector is sensitive enough, it does not report a smooth drizzle of energy. It reports discrete events. One photon arrives and triggers a response, then another, then another. Over time, the pattern builds into what we perceive as a continuous signal or image. A camera sensor, for example, gathers huge numbers of photon arrivals. Each one deposits energy into the material in a specific way, often freeing charge carriers that are then measured electronically. The image you see later on a screen may look smooth and ordinary, but underneath it lies an enormous tally of discrete energy deliveries. The eye itself works on related principles, though with biological flair rather than electronic polish. Photons enter the eye and are absorbed by molecules in the retina. That absorption triggers a chemical change which begins a cascade of events leading to nerve signals. Vision, in other words, starts with the delivery of energy by photons to specific molecules. It is hard to overstate how intimate that makes light to ordinary life. Seeing is not a vague spiritual acquaintance with the world. It is a physical process in which photons carry energy across space and hand it over to matter in highly organized ways. So how does that handover occur? Not by pouring energy smoothly into a target like water into a cup. A photon interacts with matter according to the rules allowed by the system. If the conditions are right, the photon can be absorbed. In absorption, the photon's energy is transferred to the material, often by exciting an electron, raising an atom or molecule to a higher state, or contributing to some larger scale effect such as heating. Once absorbed, the photon as that particular quantum excitation no longer exists. Its energy has become part of the state of the matter it interacted with. This is one of the most important moments in the whole story. A photon carries energy across empty space, but the carrying ends in an interaction. The energy does not just float onward and remain owned by the photon after the handoff. The process is complete. The photon is absorbed, and the receiving system changes. In some cases, the result is straightforward heating. Light strikes a dark surface. The photons are absorbed by electrons and atoms in the material. Their energy is redistributed among the microscopic degrees of freedom of the matter, and the temperature rises. That ordinary warming of a surface in sunlight is one of the clearest demonstrations of energy transfer by photons. The light travelled through space, reached the material, and left behind energy that became thermal motion. In other cases, the result is more selective. A solar cell does not merely get warmer, though it does some of that as well. It is designed so that absorbed photons can excite electrons across an energy gap in the semiconductor, creating charge carriers that can be directed into an electrical current. Here the energy carried by photons is not simply lost into random thermal motion straight away. It is captured in a way that does useful electrical work. The photon arrives with enough energy, the material structure permits the right transition, and the result is a controlled transfer that powers devices, lights indicators, and occasionally gives you the false confidence that your battery troubles are over. A laser striking material reveals another side of the same story. If enough photons of appropriate energy are delivered with sufficient intensity, the material can be heated, excited, or altered in very precise ways. Laser cutting, scanning, surgery, measurement, and communication all depend on photons delivering energy in tightly controlled forms. The empty space between laser and target does not dilute the mechanism itself. The photons propagate through vacuum or air and then interact where needed. Again, the carrying is clean because it relies on field propagation, not on a bulky transport medium. Momentum also belongs in this discussion, because energy transport by photons is not the whole story. Photons carry momentum as well, and that means when they are absorbed or reflected they can exert pressure. This effect is usually tiny in everyday settings, but it is real. Sunlight pushes on surfaces, laser beams can nudge small particles. Spacecraft concepts have even been designed around the idea of solar sails, large reflective structures that would gain momentum from light itself. The force is delicate, but across vast distances and long durations it becomes meaningful. This is a beautiful reminder that a photon carrying energy is never merely transporting brightness. It is participating in the full conservation of energy and momentum. That pressure can sound almost absurd the first time one hears it. Light pushing on things seems too delicate, too airy, too innocent. But innocence is not the same as weakness. A photon has no rest mass, yet it carries momentum. When reflected from a surface, the change in momentum can impart a tiny shove. Ordinary life rarely notices because much larger forces are almost always crowding the room. Still, the effect is there, patiently waiting for careful experiments or ambitious spacecraft designers. Something else worth noticing is that energy transport by photons is directional in a way that depends on how the photons were produced and how the field is arranged. A glowing bulb radiates in many directions. A laser emits in a narrow beam. A radio antenna is designed so that electromagnetic energy is sent outward in controlled patterns. The field structure, the source geometry, and the quantum properties all combine to determine how energy moves through space. Photons are not wandering aimlessly like tourists who ignored the map. Their propagation reflects the physics of the source and the surrounding conditions. This is especially clear in communication technologies. When information is sent by optical fibre, the energy carried by photons is guided through the fibre by repeated internal reflection and the optical properties of the material. The photons still carry energy as quanta of the electromagnetic field, but the environment shapes the path they can follow. In free space communication, lasers or radio transmitters direct photons outward through beams. In imaging systems, lenses and mirrors steer and focus them. So while empty space allows propagation, the structures we build can guide, filter, and control that propagation with extraordinary precision. There is also a statistical side to energy transport that becomes important whenever many photons are involved. A warm object emits huge numbers of photons in a range of energies. The total energy radiated depends on the combined behaviour of all of them. A star emits a staggering number of photons every second. The warmth you feel from sunlight is the collective effect of an enormous photon flux. Yet the fundamental transactions remain quantum ones. Large-scale radiative energy transport looks smooth because the numbers are vast, not because the discreteness has vanished. This is one of the recurring themes in physics. Continuity often emerges from an underlying grain of individual events too numerous to notice directly. At the same time, the quantum grain becomes impossible to ignore in certain situations. Very low light imaging, single photon detection, quantum communication, and sensitive astronomical measurements all force us to confront the one-by-one nature of photon arrivals. Under those conditions, energy transport no longer looks like a steady stream in the naive sense. It looks like a sparse series of discrete transfers. The same light that fills a room smoothly, when abundant, becomes a countable sequence when scarce enough. This does not mean light has changed character. It means our instruments and circumstances have become good enough to notice what was always there. Relativity adds another layer of interest. The speed at which photons propagate in vacuum is fixed, and that has deep consequences for the structure of space-time itself. Energy transport by photons does not depend on the motion of the source or observer in the simple additive way one would expect for classical projectiles. Light obeys the relativistic structure of the universe not the habits of thrown stones. That is why the photon's role in carrying energy is tied not only to electromagnetism and quantum mechanics, but also to the geometry of space-time. One cannot discuss light for long without all three beginning to gather around the same table. Even so, the central picture remains stable. A photon carries energy across empty space because it is a quantized excitation of the electromagnetic field, and that field can propagate through vacuum. The energy is not stored inside a hidden compartment, it is part of the photon state. The propagation does not require matter. The delivery occurs in interactions where the photon is absorbed, scattered, or otherwise involved in transferring its energy and momentum to matter. That simple framework explains warming, seeing, imaging, signaling, measurement, and a large part of how information from the universe reaches us. One of the nicest things about this is how it ties the cosmic and the ordinary together without changing the rules. The photon warming your desk in a sunbeam, and the photon carrying information from a distant galaxy are not fundamentally different kinds of thing. They are both quanta of the same electromagnetic field. The scale of the story changes, the source changes, the energy may change, but the underlying principle does not. That consistency is one of the reasons physics feels so solid when it is at its best. It does not need one set of rules for everyday life and another for the stars. It uses one framework broadly enough to cover both, and yet carrying energy through empty space is only half the story. A courier is not interesting for the road alone, but for the delivery. The real consequences appear when photons meet matter, because that is where energy transfer becomes chemistry, temperature, motion, vision, electricity, and structure. So the next step is not to ask how the photon survives the journey, but what exactly happens when the journey ends and light finally runs into something that can answer back. By the time a photon reaches matter, the quiet part of its journey is over. It has crossed space carrying energy and momentum without needing a material medium, and now it encounters something with structure, something full of charged particles, allowed states, vibrations, bonds, and constraints. This is where light stops being merely a traveller and becomes a participant. If the empty stretch between source and target is the road, then matter is where the conversation begins, and it turns out to be a very busy conversation indeed. What makes this meeting so interesting is that matter is not passive. A wall, a leaf, a pane of glass, a drop of water, a grain of dust, the lens of an eye, the surface of a pond, the metal in a spoon, the molecules in air, all of them respond to light according to their own internal structure. Light does not arrive and impose the same result everywhere. It asks a question, in a sense, and different kinds of matter answer differently. Some absorb, some reflect, some scatter, some transmit, some convert the energy into heat, some re-emit light of a different kind, some do several of these at once, which is part of why the visible world is so rich, and why a rainy street at night looks nothing like a dry road at noon. It is helpful to remember that matter, at the microscopic level, is full of electric charges. There are electrons, nuclei, and in larger structures there are molecules, lattices, bands, vibrations, and a whole hierarchy of ways in which charge constituents can move or be rearranged. Because light is electromagnetic, it naturally interacts with these charges. That is the key connection. A photon does not need a face, a hand, or a tiny crowbar. Its very nature makes it relevant to matter, because matter contains things that respond to electric and magnetic influences. The meeting is not accidental. It is built into the structure of the world. The simplest thing to say is that when light meets matter, one of three broad outcomes is usually discussed first. The light can be absorbed, it can be reflected, or it can pass through, often with some bending or slowing effect in the material. Those three possibilities are already enough to explain much of ordinary experience, but even they are only the beginning. Each one contains layers of detail. Absorption is perhaps the most intimate encounter. A photon arrives, interacts with the material, and its energy is taken up by the matter. Once absorbed, that particular photon is gone. It is not lurking invisibly behind the wallpaper waiting for a second performance. Its energy has been transferred into the material, often by exciting an electron, changing the state of a molecule or contributing to thermal motion. This is why dark clothing warms in sunlight, why asphalt can become painfully hot on a summer day, and why the inside of a parked car turns into a deeply regrettable choice. The photons are absorbed and their energy becomes motion and agitation among the atoms and molecules of the material. But absorption is not just heating. Sometimes it is highly selective. A red object looks red because it does not treat all photons the same way. Under white light, which contains many visible energies, the material absorbs some ranges more strongly than others and reflects or scatters the part we call red. That means colour is not something painted into the photon like dye in a bottle, nor is it purely a trait of the object in isolation. It emerges from the meeting between the incoming light and the material. The object is effectively sorting photons by energy and sending some onward while taking others in. A ripe tomato is not broadcasting redness from a hidden internal lantern. It is interacting with incident light in a way that lets red photons reach your eyes more readily than others. This alone is enough to make daily life feel slightly more advanced than it looks. Every time you recognize colour, you're witnessing a selective negotiation between light and matter. The blue of the sky, the green of leaves, the orange glow of a sodium street lamp, the glossy white of paper, the deep black of velvet, all of these depend on the precise ways different materials absorb and release different parts of the electromagnetic spectrum. What feels immediate to vision is, at the microscopic level, a highly specific set of interactions. Reflection seems simpler at first, but it too has hidden depth. When light reflects from a surface, it is tempting to imagine photons behaving like tiny rubber balls bouncing off a wall. That image can be serviceable for quick intuition, but it misses most of the real story. Reflection is a collective electromagnetic response of the material. The incoming light drives charges in the surface, particularly electrons, and those charges respond in a way that produces outgoing light. In polished metals, for instance, electrons can move rather freely, and this helps produce strong reflection across a broad range of visible light. A mirror looks almost magical in its reliability, yet its action comes from countless microscopic charges responding coherently to the incident electromagnetic field. That coherence matters. A good mirror preserves image information because the reflected light leaves in a very orderly way. A rough wall also reflects light, but the microscopic irregularities of its surface send the light in many directions. This is called diffuse reflection. It is why you can see the wall from different angles, while a mirror sends a more organised image. The difference between a matte painted surface and a polished one is, in large part, the difference between disordered and orderly redirection of light by matter. Transmission sounds as if light simply ignores the material and passes through politely, but that is not what happens either. In a transparent material such as clean glass, photons are not gliding through wide empty corridors untouched. The electromagnetic field interacts with the charges in the material, and the overall result is that light continues onward, with a changed effective speed, and often a changed direction if it entered at an angle. This is refraction. It is why a straw in water appears bent and why lenses can focus light. The material does not merely get out of the way, it responds to the light, and, through that response, alters the propagation. That process can sound suspiciously like a photon being repeatedly absorbed and re-emitted at every step, and while that image is sometimes offered in simplified explanations, it can mislead if taken too literally. The more accurate picture involves the collective response of the electromagnetic field and the electrons in the medium, leading to a new overall wave propagation with a different phase speed. At the level of detailed quantum interactions, one has to be careful about how the process is described, but the larger lesson remains clear. Transparent matter is not empty to light. It is structured in a way that allows light to continue through while reshaping its behaviour. Water gives an especially beautiful example because it does so many things at once. It can reflect, transmit, refract and scatter. A calm pond reflects the sky. The same pond lets you see stones below the surface if the angle is kind enough. Waves distort the images. Suspended particles scatter the light. Sunlight entering water is bent. Blue and green often dominate in certain depths and conditions. If you look at a glass of water on a table, you are looking at a laboratory of light and matter that just happens to be pretending to be ordinary. Scattering deserves special attention because it explains some of the most familiar visual effects in the world. Scattering happens when light is redirected by particles or fluctuations in matter. The atmosphere is full of molecules that scatter sunlight. Because shorter visible wavelengths are scattered more strongly under many ordinary conditions, the sky looks blue during the day. At sunset, when sunlight passes through a longer stretch of atmosphere, much of the shorter wavelength light has been scattered out of the direct path, leaving more reds and oranges in the light that reaches the eye from the direction of the sun. It is difficult to improve on a sunset as a public demonstration of light meeting matter. The whole sky becomes an experiment in atmospheric scattering, and nobody even has to wear goggles. Clouds tell a different scattering story. The droplets in clouds are much larger than individual air molecules, and they scatter light more uniformly across visible energies, which is why clouds look white or grey rather than blue. Smoke, fog, dust, milk, frosted glass, all of these produce their own varieties of scattering. The world is full of materials that do not simply absorb or reflect, but reroute light in complicated ways. That rerouting affects appearance, visibility, colour and mood. A foggy street under lamps feels different from the same street in dry air, not because the lamps changed, but because the matter in the air now answers the photons differently. Then there is the photoelectric effect, one of the most historically important examples of light meeting matter. When light of sufficiently high photon energy shines on certain materials, it can knock electrons free. This result was a crucial clue in establishing that light must come in quanta, because the effect depends on the energy of individual photons, not merely on total brightness in the classical sense. A flood of low-energy photons cannot always do the job, while a sparse arrival of higher energy photons can. Matter, in this case, is not responding to light as a smooth wash. It is responding to discrete deliveries. One photon arrives with enough energy, and an electron is ejected. The elegance of the effect lies in how sharply it reveals the quantum conversation between light and matter. That conversation becomes even more varied in atoms and molecules. A photon can be absorbed and raise an electron to a higher energy state. A molecule can be excited into new vibrational or rotational motion. In some cases, the excited system later releases a photon again. Fluorescence is a good example. A material absorbs light at one energy, and then emits light at a lower energy after some internal rearrangement and loss. That is why certain substances glow under ultraviolet light. The incoming photons are not simply bounce back unchanged. Matter takes them in, reshuffles the energy internally, and sends out new photons with a different character. It is less like a ball bouncing off a wall, and more like a package being opened, repacked, and sent on under a new label. Phosphorescence goes a step further by delaying the release. Some materials absorb energy and then re-emit light slowly over time. Glow-in-the-dark objects depend on this. The photon arrives, the material stores the energy in a metastable state, and light is released later. This is one of the gentlest reminders that the story of light does not always end at the moment of contact. Matter can take the energy and make the consequences linger. Photosynthesis is one of the grandest examples of all, not because it is rare, but because it is so foundational. In plants, pigments such as chlorophyll absorb photons and use that energy to drive the chemistry that stores solar energy in molecular form. Nearly every complex food chain on Earth depends on this meeting of light and matter. A photon born in the sun can end its journey by helping a leaf carry out the first step in a process that eventually feeds forests, animals, and people. It is difficult to think of a more successful delivery. The photons do not arrive with tiny instructions attached, but the structure of the leaf is such that their energy can be captured and directed into chemistry with astonishing effectiveness. Vision too belongs in this category. The retina is not just illuminated, it is activated through specific molecular changes triggered by absorbed photons. In dim enough conditions, the human visual system can respond to remarkably small numbers of photons. That means the meeting of light and matter inside the eye is, in a very literal sense, the beginning of seeing. The external world does not pass itself directly into consciousness. Photons strike matter in the retina, chemistry changes, signals begin, and the brain does the rest. Light meeting matter is not just how objects become visible in a vague sense. It is how the visual process starts at all. Sometimes the meeting is violent enough to change the direction of the photon in a way that also changes its energy. In Compton's scattering, for example, a photon collides with an electron and emerges with reduced energy, while the electron takes some of the momentum and energy. This was another crucial piece of evidence that photons carry momentum in a very real way. It showed that light does not merely wave at matter from a polite distance. It can exchange energy and momentum with individual particles according to strict conservation laws. A meeting between light and matter can be elastic in some cases, inelastic in others, gentle here, abrupt there, but always governed by the same deep bookkeeping. The behavior of materials under light also depends strongly on structure. Metals, insulators, semiconductors, crystals, gases, liquids, biological tissues, each has its own rules of response because each arranges charges differently. In a semiconductor, photons can promote electrons across an energy gap and create mobile charge carriers, which is the basis of solar cells and many light-sensitive devices. In crystals, the symmetry of the lattice can make polarization matter enormously. In gases, individual atomic and molecular lines can dominate absorption and emission. In biological tissue, light can be absorbed by pigments, scattered by structures, and converted into heat or signal. Matter is not one thing. It is a vast library of possible replies to incoming light. That is why spectroscopy is so powerful. By examining what light a material absorbs, emits, or scatters, scientists can infer what the material is made of and what state it is in. The pattern of interaction becomes a fingerprint. Remote sensing of planets, analysis of stars, chemical identification in laboratories, medical imaging, quality control in manufacturing. All of these rely on the fact that light-meeting matter does not produce vague, generic outcomes. It produces structured responses that reveal the identity and condition of the matter involved. There is also a subtle point that becomes more important the longer one thinks about it. The material does not only respond to the light. The light that emerges can carry information about the material precisely because of how the interaction happened. A reflected beam tells you something about surface structure. An absorbed and re-emitted photon can reveal internal energy levels. Polarization changes can reveal strain, orientation, or molecular handedness. Scattering angles can reveal particle size. The outgoing light is not merely what is left over after the material has had its turn, it is evidence. In this sense, nearly every visible thing is constantly publishing a report about itself in photons. That is also why the world does not look flat or uniform. Texture exists because light interacts differently with rough and smooth surfaces. Transparency exists because some materials allow certain photons through while others do not. Gloss exists because some surfaces preserve directional reflection. Color exists because absorption and emission are selective. Opacity exists because too many photons are absorbed or scattered to let an image pass through. Even shadow is just the absence of direct photon arrivals in a region where an object has blocked or redirected the light. Everywhere you look, appearance is the result of negotiation, not announcement. and like most negotiations in physics, the rules can become very strict at small scales. Not every photon can be absorbed by every atom. The energy has to match an allowed transition, or the probability has to be favourable in the relevant process. This selectivity is why atoms and molecules have characteristic spectra. Matter only accepts certain photonic offers under certain conditions. It is as though the microscopic world has a very clear policy on acceptable transactions. The universe is surprisingly choosy when properly examined. All of this tells us that the meeting between light and matter is not a single kind of event but a whole family of possible encounters. Light can heat, reveal, push, excite, ionize, trigger chemistry, generate electricity, produce images, alter materials, or simply glance off and continue. Matter can absorb, reflect, scatter, transmit, fluoresce, polarize, focus, delay, or transform what arrives. The visible world is the sum of these replies, happening ceaselessly and mostly without our noticing. There is a quiet pleasure in that realization. A sunbeam on a floor, the shine on a spoon, the colour of an apple, the brightness of a phone screen, the glitter of frost, the softness of fog, all of them are not separate miracles but variations on the same underlying event. Photons meet matter, and matter answers according to its structure. That answer becomes warmth, colour, signal, glare, image, or life itself depending on the circumstance. And once you begin to see the world that way, another question starts to feel unavoidable. If photons can be born in one process, travel through empty space, arrive carrying energy and momentum, and then interact with matter in ways that depend so delicately on state and structure, what happens when photons are not merely encountering matter independently, but are linked to one another in ways that seem to ignore the ordinary boundaries between separate events? That is where the story takes a distinctly stranger turn, because light does not only meet matter. Sometimes photons meet each other through the logic of quantum correlations, and what follows is far more social than the old particle picture ever prepared us for. If light meeting matter already made the photon seem more interesting than any ordinary tiny object has a right to be, entanglement takes that interest and pushes it into territory where even careful common sense begins looking over its shoulder. Because up to this point, even when the photon has been strange, it has often still felt like something that can be followed on its own terms. It is born in a process, it carries energy, it interacts with matter, it has polarization and spin, and although none of those things behave in a fully classical way, they can still be discussed one photon at a time. Entanglement changes the mood. It asks us to stop thinking of photons as merely individual participants and start thinking about pairs or groups whose properties are linked in a way that cannot be reduced to each one carrying a private set of instructions from the start. That is why the phrase strange social life of photons is not really a joke, or at least not only a joke. Photons do not have feelings, preferences, grudges, or plans. They do not exchange gossip in fibre optic cables, but they can be prepared in states where what happens to one cannot be fully described without reference to the other, even when the two are far apart. They are not social in the human sense. They are correlated in a way that classical imagination does not handle gracefully. The first thing to say is that entanglement is not just any correlation. Ordinary life is full of correlations. If you put a pair of matching gloves in separate boxes and send them to different cities, then opening one box and finding a left glove tells you the other box contains a right glove. That is a correlation, but it is a very classical and frankly rather dull one. The gloves already had their handedness all along. Opening the box does not create it. It just reveals what was always there. If entangled photons behave like that, the subject would still be interesting enough to keep a laboratory employed, but it would not have caused such profound trouble for our understanding of reality. The difference is that entangled quantum systems can produce correlations stronger and subtler than any arrangement of pre-assigned hidden properties seems able to explain, at least if we also insist on certain intuitive ideas about locality and independent reality. That is the heart of the matter. The photons are not merely matching in some ordinary way. They are linked through a shared quantum state. Their properties are not always fully definite in the classical sense before measurement, yet when measurements are made, the results are correlated with astonishing precision, according to the structure of that shared state. Photons are especially good for studying entanglement, because they are easy to produce in controlled quantum states, easy to send over long distances, and relatively gentle to work with compared with some other quantum systems. They also allow the relevant properties, especially polarization, to be prepared and measured with exquisite care. In many famous experiments, entangled photon pairs are created so that their polarizations are correlated in a quantum way. One photon goes one way, the other goes another, and then measurements are made at separate detectors. The results are not random in the simple everyday sense, and not predetermined in the glove sense either. They reflect the shared quantum state of the pair. To understand how such pairs can arise, it helps to recall that photons are born in processes not taken from storage. Some of those birth processes can naturally produce linked photons. One widely used method involves sending light into certain special crystals. Under the right conditions, a higher energy photon interacting with the crystal can give rise to a pair of lower energy photons whose properties are correlated. The process must obey conservation of energy and momentum, and depending on the setup, the resulting photons can emerge entangled in polarization or other variables. This is not the crystal acting like a small factory with tiny workers assigning matching labels. It is a quantum process in which the pair is described together from the very beginning. That togetherness is the important point. If the two photons are entangled, then the full physical description belongs to the pair, not separately to each photon in the ordinary way. Each individual photon may not have its own complete standalone account of a particular property prior to measurement. Instead, the pair has a shared state that encodes the possible outcomes and their correlations. That is difficult to picture because our ordinary habits are built on objects having their own private attributes. A cup is heavy or light. A shirt is blue or grey. A coin is heads or tails when lying on the table. Entangled photons resist that kind of independent bookkeeping. Polarization offers a good way into the problem because it is so accessible experimentally. Imagine a source that emits pairs of photons in such a way that their polarizations are linked. If one photon is measured with a polarization filter set at a particular angle, the outcome for the other photon, measured far away, is correlated in a way that depends on both the shared entangled state and the chosen measurement settings. If the setup is arranged correctly, repeated measurements produce statistical patterns that cannot be accounted for by assuming each photon carried a pre-written answer sheet for every possible filter orientation. That claim is not philosophical embroidery. It is the outcome of decades of careful experiments inspired by deep theoretical work on the foundations of quantum mechanics. This is where John Bell enters the story, though gently, because even Bell would probably not want to interrupt a sleepy science narration more than necessary. Bell showed that if the world behaved according to certain local hidden variable ideas, then correlations between separated measurements would have to satisfy specific limits. Quantum mechanics predicted violations of those limits for entangled systems. Experiments were then designed to test the issue. Over time, the results overwhelmingly favoured the quantum prediction. Entangled photons really do display correlations that outrun what those local hidden variable explanations could provide. That statement is easy to say and hard to feel. The reason it is hard to feel is that our brains keep trying to rescue the glove picture. Surely, one thinks, the photons must each have carried the relevant information from the start. Surely the measurement simply uncovers what was already there. Yet the pattern of experimental outcomes says that such a simple rescue will not do, at least not if one keeps the usual assumptions about locality and independent pre-existing values. The universe is more selective and more interconnected at the quantum level than common sense had anticipated. Now, whenever entanglement is described, Someone rightly worries that it sounds as though information is being sent instantly from one photon to the other. One is measured here, and somehow the other knows what to do there. That language is tempting, and it is also dangerous. Entanglement does not allow faster-than-light messaging in the ordinary practical sense. You cannot use an entangled pair to send a secret note instantaneously to another planet. The local outcome at either detector still appears random when viewed alone. It is only when the results from both sides are later compared that the deeper correlation becomes apparent. So entanglement is not a telegraph with unrealistic ambitions. It is a non-classical linkage in the structure of joint outcomes. This distinction matters because without it the whole subject turns into a parade of misleading headlines. Entangled photons are not chatting across space. Nothing useful in the ordinary signalling sense is being transmitted faster than light. What is remarkable is that the shared quantum state produces correlations that cannot be decomposed into the sort of local private properties we would have expected. The world is not violating every rule at once. It is violating a particular set of classical expectations about how separate systems ought to carry their own complete descriptions. There is a wonderfully uncomfortable lesson hiding in that. We like to imagine that objects have well-defined properties independently, and that distance protects separateness. Entanglement does not abolish those ideas everywhere, but it does show that at the quantum level the notion of separateness can be less absolute than our habits suggest. If two photons are entangled, then in an important physical sense the pair has a unity that survives spatial separation. Not unity in a mystical sense, not cosmic friendship. Unity in the exact technical sense that the state of the pair is not reducible to the states of its parts alone. That is why the photon becomes such a good guide to the foundations of reality. Light is easy to dismiss as familiar until it starts doing things like this. A beam across a room seems innocent enough, but prepare the photons carefully and they reveal that the universe is not built from independently labelled pebbles after all. It is built from quantum states that can span more than one system at once. One reason photons are so central in entanglement experiments is that they travel well. Matter-based quantum systems can be delicate and difficult to separate cleanly over long distances. Photons, by contrast, are natural travellers. They can be sent through optical fibres, across laboratories, over open-air links, and even between ground stations and satellites. That has made them the preferred messengers for many quantum communication experiments. A pair of entangled photons can be created together, then sent in different directions, and their polarization measurements later compared. This has allowed increasingly strict tests of quantum mechanics and increasingly ambitious demonstrations of quantum technology. And this is where the strange social life of photons becomes not only a philosophical curiosity, but a practical resource. Quantum cryptography can use entangled photons to establish secure keys in ways that reveal eavesdropping. Quantum teleportation, despite its alarming name, uses entanglement to transfer the state of a quantum system from one place to another with the aid of ordinary classical communication. No object disappears in a glittering beam. No person is reassembled from good intentions. What is transferred is quantum state information, and photons often play a starring role in the process because they are so good at carrying and preserving delicate correlations. There is something deliciously unfair about that, a concept so strange that it once seemed like an embarrassment for the interpretation of quantum theory has become a basis for new technologies. The universe takes one of the deepest philosophical puzzles of the 20th century and calmly turns it into an engineering opportunity. That feels like exactly the sort of thing the universe would do. Still, one must not romanticize entanglement too carelessly, because it is fragile in many contexts. Quantum states can lose coherence when they interact too much with the environment. This is called decoherence, and it is one of the main reasons the everyday world does not look entangled in obvious ways all around us. Large systems are continually interacting with countless surrounding degrees of freedom, and the clean quantum relationships that are so visible in carefully isolated experiments become washed out. Entanglement is not rare in the microscopic world, but stable, controllable entanglement is precious. It must often be protected from noise, loss, and unwanted interactions. Photons help here as well because they can, under the right conditions, preserve quantum information long enough to be useful. They do not rest. They are not burdened with a complex internal structure like large molecules. They can travel at the natural speed set by the electromagnetic field and maintain carefully prepared polarization states across significant distances. This makes them excellent candidates for linking quantum devices and for probing the limits of non-classical behavior. Another lovely feature of entangled photons is that they force us to think statistically rather than dramatically. Popular imagination prefers stories in which one particle instantly commands another and everyone gasps. Real experiments are more patient and more convincing. One measures many pairs. One varies analyzer settings. One gathers large data sets. The miracle, if one wants to use that word carefully, is not in a single theatrical event, but in the stable pattern across many events. Quantum mechanics predicts specific correlations, and the experiments match them. That calm agreement between theory and observation is much more impressive than any single sensational image. The statistical nature of the evidence also helps with an important misconception. It is not that each measurement reveals a hidden definite polarization that had merely been waiting under a cloth. Rather, the entangled state determines the probabilities of different joint outcomes for different measurement settings. The full pattern across many trials is what reveals the genuinely quantum nature of the link. One can easily mislead oneself by thinking too much about one pair at a time. Entanglement shows its deepest character in ensembles and correlations. There is also a conceptual humility that comes with all this. For centuries, the dominant picture of physical reality leaned heavily on separable objects with their own local properties. That picture still works beautifully in a vast range of human experience. It is not wrong so much as incomplete. Entangled photons show that the quantum world does not always respect the boundaries our categories prefer. Sometimes the best description belongs to the relationship before it belongs to the individuals. In ordinary life, this feels unusual. In quantum theory, it is simply part of the rules. One may even say that entanglement teaches a new kind of realism, though perhaps not the one classical intuition wanted. It is not telling us that reality is vague or imaginary. The correlations are very real. The experimental outcomes are crisp. The devices function. What changes is our idea of what must count as physically basic. Independent local attributes are not always enough. Joint quantum states have to be taken seriously as elements of reality. That's a more relational picture than many older instincts would have chosen, but the photons do not seem bothered by our discomfort. This becomes especially striking in delayed choice and quantum eraser-style experiments, where the way information is arranged or erased can affect which patterns emerge when entangled photons are analysed. These experiments are often described in ways that make them sound as though the past is being rewritten, which is not a helpful way to keep everyone calm. A better way to say it is that quantum predictions concern whole experimental arrangements and the correlations among recorded outcomes. Entanglement makes it dangerous to assign a naive classical story to each photon independently before the measurement context is complete. The lesson is not that time has collapsed into mischief. The lesson is that quantum systems do not always tolerate classical narrative shortcuts. Even without venturing into those more elaborate experiments, the core message remains plenty strange enough. A pair of photons can be created in such a way that neither is fully described on its own, yet together they possess a joint state whose correlations show up later in separated measurements. The pair behaves less like two little objects carrying separate identities, and more like one extended quantum fact expressed in two places. Again, not a mystical one, not a spiritual one, just a physical one, but a physical fact strange enough to have changed our understanding of what physical facts can be. And because photons travel so well, these quantum relationships can stretch astonishingly far. Entanglement has been demonstrated over long terrestrial distances and even through space-based links. This gives the whole subject a scale that is hard not to appreciate. Something born in a tiny crystal in a laboratory can produce correlations tested across kilometers of separation, all while respecting the same quantum rules that govern the smallest interactions of light and matter. The local and the large scale meet through the quiet competence of photons. There is an odd comfort in that, perhaps because it turns the subject away from pure abstraction and back toward the visible world. Light, which we normally think of as what makes things clear, is also what reveals that reality is not as classically clear as we assumed. The same entity that lets you see a leaf or a lamp can also be prepared to expose the incompleteness of local, hidden variable intuitions. Photons illuminate objects, and then, without apology, illuminate the limits of our metaphors. It is tempting at moments like this to ask whether entanglement means everything is secretly connected to everything else in one enormous universal embrace. Physics is usually less sentimental than that. Entanglement can exist widely, yes, and the quantum state of complex systems can be extraordinarily rich, but useful, controllable entanglement is specific and must be treated carefully. The lesson is not that all boundaries are illusions in some vague way. The lesson is that some boundaries we thought were fundamental are not fundamental in the way classical thinking imagined. That is subtle, less marketable, and much more interesting. So the strange social life of photons teaches us that light is not only a carrier of energy and information in the ordinary sense, it is also one of the best windows into the relational structure of quantum reality. Entangled photons show that separate particles can share a state that cannot be broken into independent local pieces. They reveal correlations stronger than classical hidden instructions can provide. They do this without allowing faster-than-light messaging, without breaking the practical structure of causality, and without ever becoming less precise than the experiments that test them. It is one of the finest examples in science of a result that is both deeply unsettling and exquisitely well established. And once one has accepted that photons can be born together, travel apart and still remain linked in this non-classical way, the idea of a lone photon crossing a huge distance starts to feel newly dramatic as well. Because even without a partner nearby, every photon has a story. Some are born in stars, some in lamps, some in atoms, some in galaxies unimaginably far away, and eventually some small fraction of them complete journeys that end in eyes, detectors, leaves, mirrors, or telescopes. After entanglement, the next question almost asks itself. What is it like for light to travel from a source across the world, or across the atmosphere, or across interstellar space, and finally arrive at the one place where the universe becomes visible to a particular living observer? There is something quietly astonishing about the fact that vision begins so far away from you. When you look at the world, it is easy to feel as though sight happens where you are, as though the eye reaches out and simply takes hold of what is nearby. It does not feel like a long-distance affair. It feels immediate. The tree is there, the cup is there, the moon is there, the lamp is there, and your eyes appear to gather them in without delay. But what actually happens is much more indirect and much more interesting. What reaches you is not the object itself. What reaches you is light, and often that light has already had quite a life before it arrives. For some photons, the trip is short and domestic. A bulb in the room emits them, and they travel a few meters before ending in paint, fabric, paper, glass, or skin. A screen sends them straight to your eyes from the device in your hand. A candle flame throws them across the table. These are modest journeys, but even they are enough to remind us that seeing is never the direct presence of things in the mind. It is always an arrival. The world becomes visible because photons travel from a source, or from a source after reflection, and then meet your retina. There is always a journey, even when it is only the width of a room. Then there are the less modest journeys. Sunlight reaches you after crossing the space between Earth and the Sun. The starlight you see at night may have been travelling for years, decades, centuries, or far longer depending on the star. The light from a galaxy may have begun its journey long before there were people to ask what a galaxy is. Some of the visible world is fresh and local, Some of it is delayed by distance. To see is to accept information from the past, sometimes the immediate past, sometimes the deep past. The eye is less a window than a receiving station. That is one of the reasons astronomy feels so intimate despite its scale. Looking out is also looking back. A photon that reaches your eye from a star did not leave that star at the moment you noticed it. It left earlier, sometimes much earlier, and carried its energy through space until at last it met matter in your body. The star you see is never exactly the star as it is right now in some universal present. It is the star as reported by arriving photons. Light makes the universe visible, but it also makes it historical. The journey often begins in a place far more turbulent than the calm image at the end might suggest. Take a star. From Earth, a star can look like a neat pinprick, as if nature had been very sparing with the lighting budget. But inside a star there is no such neatness. In the core, extreme temperatures and pressures enable nuclear reactions that release enormous amounts of energy. That energy does not simply exit in a straight polite line. In dense stellar interiors, photons are absorbed and re-emitted over and over again. They scatter, change direction, and are continually caught up in interactions with charged particles. The path outward is slow and chaotic. Energy may take an extraordinarily long time to work its way from the core to the surface. By the time a photon finally escapes the outer layers of the star and begins a cleaner passage through space, it is part of a very long history of interactions. That history matters because it reminds us that the photon arriving at your eye from the sun is not a tiny hero that raced untouched from the solar core like an overachieving messenger. The light that finally leaves the surface is the late-stage expression of energy that has been repeatedly transformed and re-released within the star. The identity of individual photons is not preserved in some romantic classical way through that entire process. What persists is the transport of energy outward through many births and endings of photons until some of them at last reach open space and can travel freely for a while. Once in space, the journey becomes cleaner, though not always entirely uneventful. Interplanetary space is mostly empty, but mostly empty is not the same as perfectly empty. There are particles, fields, dust and plasma here and there, though sparse enough that many photons can pass without incident. That sparseness is what makes astronomy possible. If space were as cluttered as a foggy kitchen full of steam, stars would be much harder to admire, and the universe would be much less willing to explain itself. The relative emptiness of space allows photons to carry information over great distances without being absorbed or scattered into uselessness. Still, even near Earth, light has one more major obstacle or invitation depending on your mood: the atmosphere. For those of us living comfortably under it, the atmosphere feels like background. It is air. It is weather. It is what gives clouds somewhere to loiter. But for photons arriving from the sun, the moon, planets and stars, the atmosphere is an active participant in the final stage of the journey. It reflects, absorbs, bends, and scatters. It sorts light by wavelength and angle. It turns the sky blue, sunsets orange, stars twinkly, and distant landscapes hazy. The atmosphere is not simply sitting there while light passes through. It is editing the incoming report. The blue of the daytime sky is one of the gentlest examples. Sunlight contains many visible energies, but air molecules scatter shorter visible wavelengths more strongly under ordinary conditions. As a result, when you look away from the sun in the daytime, the light reaching your eye from many parts of the sky has been scattered and is rich in blue. That means much of the visible dome above you is not direct sunlight in the strictest sense. It is sunlight that has already had a small encounter with matter. By the time it reaches your eye, it has been rerouted by the atmosphere. A clear sky is a vast display of photons on their second plan. At sunset, the geometry changes, and so does the story. Sunlight crossing more of the atmosphere loses more of its shorter wavelength component from the direct path. The remaining light looks warmer, richer in red and orange. Clouds, dust, and aerosols can amplify the effect, giving evenings their remarkable range of colour from gentle peach to rather theatrical crimson. A sunset is not paint. It is path length, scattering, selective loss, reflection from particles and droplets, and the willingness of your retina to turn those arriving photons into an experience that can make a person stop walking mid-sentence. Moonlight is another case with its own quiet charm. The moon does not produce visible light of its own in the ordinary sense. What reaches your eye from the moon is mostly sunlight reflected from the lunar surface. Those photons began at the sun, travelled to the moon, interacted with rock and dust there, and then continued on toward Earth. By the time moonlight reaches you, it has already lived 2 landscape lives, one solar and one lunar. It is less intense because much of the original light was not redirected your way, but the principle is the same. Seeing the moon means receiving photons with a travel history. Starlight goes farther still, and that distance changes the emotional tone of the story even if the physics remains disciplined. A star you see tonight may be a few light years away, which means the photons reaching you left before the headlines, worries, errands, and forgotten passwords of recent years. More distant stars report older conditions. A galaxy may be so far away that its light began travelling when human civilization looked very different, or did not yet exist in its present form at all. This is not poetic exaggeration. It is the ordinary meaning of finite light speed. The cosmos is visible because photons move, but the same rule means the cosmos is always presented with delay, and still, after all that, the final part of the journey is perhaps the most intimate. A photon reaches the eye. It enters through the cornea, passes through the pupil, and is focused by the lens onto the retina at the back of the eye. Already this alone is a marvellous piece of biological engineering. The eye is not merely a passive hole through which light falls. It is an optical system with transparent materials, curved surfaces, adjustable aperture, focusing mechanisms, and a layered neural detector. Long before the brain begins making sense of anything, the eye has already done a large amount of careful physical work on the incoming light. The cornea and lens bend the light so that an image is formed on the retina. If the focusing is right, the world is sharp. If not, glasses, contact lenses, or a resigned squint may be required. But however the optics are tuned, the principle remains the same. The eye guides photons onto a light-sensitive surface. That surface is populated by photoreceptor cells, rods and cones, which contain molecules capable of changing state when they absorb photons. Here the journey of the photon ends in the most literal sense. It is absorbed, and in that absorption the process of vision begins. That molecular moment is easy to overlook because it is so small, and because what we notice is the final experience of seeing, not the microscopic trigger. Yet it is one of the most significant meetings of light and matter in your life. A photon enters the eye, reaches a photoreceptor, and is absorbed by a pigment molecule. That absorption changes the shape of the molecule. The molecular change sets off a biochemical cascade. The cascade alters the electrical behaviour of the receptor cell. Signals are passed to other cells in the retina, then along the optic nerve, and eventually into the brain, where further processing constructs what you actually experience as sight. In other words, the world you see is not made out of objects entering your mind. It is made out of light ending its journey in chemistry. This is a deeply physical process, though not a crude one. The retina is not a sheet of simple light meters. It is already doing analysis. Some cells respond to contrast, some to edges, some to temporal changes. Information is compressed and processed before it even leaves the eye. By the time the brain receives the signal, it is not being handed raw photons. It is receiving the consequences of many photon absorptions, already shaped by biological circuitry. Vision is partly optics, partly chemistry, partly electrophysiology, and partly neural interpretation. The photon begins the chain, but what we call seeing is the work of the whole system. That system also explains why different conditions feel so different. In dim light, rods dominate. They are more sensitive and better suited to low photon counts, but they do not give rich colour. In brighter conditions, cones take over more strongly, and colour perception becomes vivid. This means the character of sight depends partly on how many photons are arriving and at what energies. Twilight has its own look because the photon budget and the receptor response are changing. Noon and midnight are not simply brighter or darker versions of the same world. They are different modes of visual conversation. Colour vision adds another layer of sophistication. Different cone cells respond preferentially to different ranges of visible light. A surface illuminated by white light reflects or scatters certain photon energies more than others, and the pattern of cone activation becomes part of the basis for perceived colour. Your experience of red or green or blue is not located inside the photon itself like a label, nor is it fully inside the object in isolation. It emerges from the relation among the incoming light, the object's interaction with that light, and the biology of the visual system. Colour is one of the great collaborations between external physics and internal interpretation. This means that every glance you take is already a solved inverse problem of ridiculous complexity. The world sends light. Surfaces have mixed reflectance properties. Illumination varies. Shadows shift. Atmospheres scatter. Objects move. Eyes tremble slightly. Yet the brain builds a stable, useful picture from these incoming photon-driven signals. It discounts some changes, emphasizes others, estimates edges, tracks motion, fills in gaps, and creates continuity. All because photons completed their journeys and left traces in matter that biology learned how to read. There is something very moving about that once one pauses long enough to notice it. A photon may begin in a star, survive an immense crossing, pass through atmosphere, enter an eye, end in a retinal molecule, and contribute to a moment of awareness. A tiny quantum event becomes part of a face recognized, a page read, a road navigated, a memory formed. The universe does not merely shine. It arrives and becomes experienced through matter arranged in the right way. Even artificial instruments imitate this basic truth. Cameras, telescopes, microscopes, and sensors all rely on photons arriving and interacting with carefully designed materials. A telescope gathers more photons than the eye alone can, allowing fainter objects to be studied. A camera sensor converts photon arrivals into electronic signals. A microscope uses focused light to reveal structures too small for casual sight. In each case, the device extends the basic logic of vision. It catches travelling photons and transforms their absorbed energy into information. Instruments are, in that sense, artificial retinas with very specific ambitions. Telescopes are especially relevant here because they let us appreciate just how much of our knowledge depends on patient photon collection. A faint galaxy is not seen because the telescope somehow reaches out and touches it. It is seen because photons that left long ago are gathered over time by mirrors or lenses and directed onto detectors. The longer the exposure, the more photons accumulate, and the clearer the signal becomes. Astronomers are, in a very real way, professional receivers of delayed light. They work not by visiting distant worlds, but by persuading enough photons from them to arrive in an orderly manner. That also means there is a melancholy side to the story, if only a small one. If a source stops shining, its light does not vanish everywhere at once. Nearby regions stop receiving it first, distant ones later. In a universe governed by finite light speed, endings travel too. A star could be gone while its older photons still make it visible somewhere else for a time. Vision always comes with delay, and truth arrives when the photons do. This is not a flaw. It is simply how a universe with light speed as a limit has chosen to disclose itself. Closer to home, the same principle explains why mirrors show you slightly old versions of yourself, though mercifully only by a tiny amount in ordinary settings. The light from your face travels to the mirror and back. The delay is real, just too small to matter in casual life. Every view is historical. Usually the history is too brief to make anyone uneasy. Astronomical history is hard to ignore because the distances are grand enough to produce timescales that feel substantial, but the rule is the same in both cases. What you see is what photons have had time to bring. There is also a democratic quality to light's long journey. A photon does not care whether it is heading toward a telescope, a leaf, a stone, a puddle, or a sleepy person staring out a window. It propagates according to the same laws and interacts where conditions permit. The grandeur comes not from the photon's personal ambitions, but from the structures it meets. The same basic entity can trigger photosynthesis, reveal a constellation, expose a camera image, or illuminate the steam rising from tea. That continuity is one of the quiet triumphs of physics. It uses one kind of thing to explain both the sky and the kitchen, and yet for all the distance, all the scattering, all the bending, all the absorption and detection, there remains a final question hanging over the whole journey. The photon carries information, yes. It makes vision possible, yes. It links stars to eyes and matter to mind. But once we have followed light all the way from its birth through empty space and into experience, we arrive again at the larger puzzle that has been stalking us from the beginning. What does the existence of such a thing really tell us about reality itself? Because a photon is not only a practical messenger, it is also a clue, and perhaps the clearest clue in physics that the world is not built the way ordinary intuition first imagined. After everything we have followed so far, the photon begins to look less like a topic inside physics, and more like one of the places where physics quietly reveals what kind of universe we actually live in. It is small, or at least it belongs to the smallest scale of description we usually talk about with confidence, but its lessons are not small at all. The longer you stay with it, the more it starts to interfere with the old habits of thought that most of us carry around without noticing. It interrupts our ideas about what an object is, what empty space is, what it means to move, what it means to carry energy, what it means for something to be seen, and even what it means for two events to be related. That is already a lot of work for something that people often imagine as a little flash from a laser pointer. The first thing a photon reveals about reality is that the world is not built only from the sort of objects human beings find easy to picture. That may sound obvious after all this, but it is more radical than it appears. We like solids, we like edges, surfaces, interiors, and things that can in principle be held, stacked, cut, counted, and blamed for falling off shelves. Everyday life trains us to trust matter that behaves like matter at our scale. A chair is a chair because it occupies space in a very cooperative way. A spoon remains a spoon unless you do something regrettable to it. Even when we learn that matter is made of atoms and atoms of smaller pieces, the instinct remains that reality at bottom must still be made of tiny things that are object-like in the usual sense. The photon does not really allow that comfort. It is real, measurable, countable in interactions, and indispensable to the structure of the world. But it is not a little bead with a proper inside and outside. It is not a tiny torch. It is not a grain of glow. It belongs to a deeper description in which fields are fundamental, and what we call a particle is a quantum excitation of a field. That is a very different kind of reality than one built from miniature versions of billiard balls. This matters because once one photon is allowed to behave that way, the whole world stops looking quite so mechanical in the old sense. The universe is not simply a collection of little lumps moving through a blank stage. The stage itself is active. The fields are not decorative bookkeeping devices scribbled in the margins. They are part of the main cast. The photon reveals that the deep structure of reality may be better described as interacting fields with quantized excitations than as tiny hard objects wandering around in emptiness. That leads to the second lesson. Empty space is not simple nothing. In ordinary speech, nothing means an absence so complete that there is not much left to discuss. An empty box has no apples in it. An empty room has no furniture, though perhaps it has a suspicious amount of dust. But physical emptiness is not that kind of emptiness. A photon can cross vacuum because the electromagnetic field exists there, possibility of propagation is built into the structure of space itself as physics currently understands it. That means what looks like a void is not merely a blank page waiting for matter to scribble on it. It is a place where fields are defined, where light can travel, where interactions can be prepared, and where the geometry of space-time matters. This is one of those corrections that feels minor until it starts spreading into everything else. If vacuum is not crude nothingness, then the old picture of objects sitting in a passive emptiness becomes too simple. Space is not just where things are, it participates. Space-time has structure, fields inhabit it. Light reveals that directly because without such structure, the idea of a photon crossing the distance from a star to your eye would make no sense at all. The photon also reveals that energy is not always exchanged continuously in the smooth way human intuition expects. This is perhaps one of its most famous lessons, though the fame tends to hide the strangeness. Light can behave like a wave in many contexts, but when it gives energy to matter or receives energy from matter, it does so in discrete amounts. The world, at least in this domain, is not infinitely divisible in practice the way a stream of water is divided among glasses. It comes with units. Nature is willing to be smooth in some descriptions and grainy in others. That is not a flaw in the theory. That is what the evidence says. This means reality has a layered character. At large scales, things often look continuous. A beam of sunlight looks smooth. A lamp seems to fill a room with an even glow. The sky does not usually appear to arrive one photon at a time, unless your day has gone very strangely indeed. But beneath that smooth appearance lies discreteness. Count enough carefully, and the grain shows. That tells us something important about the relation between everyday experience and deeper physical description. What we perceive directly is often an average, an emergent result, a large-scale appearance produced by vast numbers of smaller events. The continuity is not false, but it is not the whole story. The photon further reveals that classical categories are useful but not final. We have spent much of this journey watching light refuse to stay obediently inside the boxes labelled wave and particle. In some experiments, the wave description is natural and powerful. In others, the particle aspect is unavoidable. Yet the deepest lesson is not that light is indecisive. It is that our old categories were built from the wrong scale of experience. A photon is not partly wave on weekdays and partly particle on weekends. It belongs to a quantum framework that can look wave-like in some respects, and particle-like in others, because both classical pictures are limited shadows of a deeper account. This is one of the most sobering and useful things physics can teach. Human categories are not guaranteed to match nature at every level. They are tools, not commandments. We invent them because they work well enough for apples, oceans, bells, smoke, rain, and moving buses. Then we discover domains where the tools bend. The photon is one of the best examples of nature asking for better language. It does not politely fit the boxes we built before we knew it existed in the modern sense. Another lesson the photon offers is that properties need not arise from hidden internal machinery. This point matters because it runs against a very old instinct. If something behaves in an organised way, we assume there must be smaller parts inside doing the work. A clock tells time because it has gears or circuits. A violin makes sound because it has strings and wood and shape. A camera works because it has lenses and sensors and processing electronics. So when a photon carries energy, momentum, polarization, and spin, one is tempted to imagine some hidden device within it. But the photon has no inside of that sort. Its properties are fundamental to its identity in the theory. They are not assembled from smaller visible components. That is a difficult lesson because it tells us explanation does not always mean reduction to tiny clockwork. Sometimes explanation means learning the correct level of description and accepting that certain features are basic there. The world may not bottom out in little machines. It may bottom out in entities and rules whose properties are not further unpacked in the same mechanical style. The photon is one of the cleanest reminders of that. It also reveals that information about reality often comes to us indirectly and with delay. This is perhaps the most human lesson of all, because it reaches beyond laboratory physics and into the way every visible moment works. You never see an object directly in the naive sense. You receive photons. Those photons have interacted with matter, travelled through space, passed through optical systems, and ended in chemical events in your retina or in some detector that extends your vision. Seeing is inference based on arriving light. That is true of a nearby cup and of a galaxy at the edge of observation alike. The difference is mostly one of scale and timing. So the photon teaches that reality is not handed to us raw, it is mediated. Not in the vague philosophical sense that everything is interpretation, and therefore nothing matters. Quite the opposite. The mediation is physical and precise. We know the world through interactions. Photons arrive, matter responds, detectors record, brains interpret, telescopes accumulate, cameras count, spectra reveal. A large part of science consists of learning how to read these mediated arrivals correctly. That point becomes especially powerful in astronomy. Light from distant objects is old light. The universe we see is a historical record delivered photon by photon. The sky is not showing us what is happening everywhere now in some universal simultaneity. It is showing us what had time to arrive. The photon therefore reveals that time and observation are inseparable in a universe with finite light speed. Every view is delayed. Usually the delay is tiny enough to ignore. Sometimes it is measured in years, millennia, or billions of years. The rule is the same in all cases. The photon also reveals that relationships can be as fundamental as individual things. This becomes unavoidable once entanglement enters the picture. Classical intuition prefers independently defined objects carrying their own complete private set of properties. Entangled photons resist that picture. The full description belongs to the joint state, not simply to the two taken separately in the old way. That tells us reality is not always composed from independently labelled units that merely happen to interact. Sometimes the relation itself is part of what is physically basic. This is an extraordinary idea because it means separateness is not always what it first appears to be. Two photons can be far apart in space and still require a shared description. They do not thereby become magical or capable of sending messages faster than light. But they do show that the old idea of each object carrying a complete local script from the start is not enough. The universe is more relational than classical habits expected. The photon reveals that in a particularly sharp way because entanglement experiments with light are so clean and so well studied. Then there is the matter of measurement, which the photon brings into view without allowing cheap mysticism to take over. A photon can be described probabilistically in quantum theory, and the outcomes of certain measurements are not fixed in the classical way before the measurement context is specified. That does not mean consciousness creates reality by glaring at it sternly. It does mean that interaction matters. A measurement is not a passive glance. It is a physical event in which systems couple and a result is recorded. The photon reveals that our knowledge of reality is tied to the structure of those interactions, not merely to detached observation from nowhere. This is one of the reasons quantum mechanics feels so uncomfortable to common sense. We want the world to have a fully definite classical script whether or not anything interacts with it. Physics seems to say that in some domains the better question is not what a system was doing in secret all along, but what the theory predicts for the results of possible interactions. That is not a retreat from realism. It is a revised realism, one grounded in what can be prepared, transformed, and measured. The photon also reveals that the everyday world is built from immense repetition of very small events. A wall looks steady because huge numbers of photons are reflecting and scattering from it all the time. A warm surface is warm because countless microscopic energy transfers have occurred. A photograph is an ordered record of large numbers of photon detections. A beam looks continuous because the arrivals are abundant. The smooth, visible world is, in many respects, a statistical achievement. Reality at our scale is what the microscopic world looks like when it's repeating itself so faithfully and so often that the grain disappears into texture. That is a reassuring thought in its own way. The quantum world is strange, but it is not chaotic in the sense of being lawless. The reason large-scale reality is stable is precisely because the microscopic laws are so reliable. Photons reveal this beautifully. Individual events can be probabilistic, yet the overall behaviour of large numbers is astonishingly dependable. That is why we can build optics, telecommunications, imaging systems, lasers, telescopes and ordinary windows without needing to negotiate separately with each incoming quantum. Nature does not behave randomly in the vulgar sense. It behaves statistically with exquisite consistency. The photon further reveals that reality is deeply economical. The same entity that explains warmth from the sun, the colour of leaves, the function of a laser, the blue of the sky, the operation of a camera, the chemistry of vision, and the testing of quantum foundations is the same photon. There is something almost sternly elegant about that. The universe is not using one special kind of light for biology, another for astronomy, another for human eyes, and another for quantum experiments. It is using one electromagnetic framework across an enormous range of scales and circumstances. That unity is one of the strongest signs that physics is not merely inventing convenient stories. It is finding real structural simplicity beneath apparent variety. And yet the photon also teaches humility, because for all we know about it, it still resists complete intuitive domestication. We can calculate its behaviour with extraordinary success. We can manipulate it, count it, entangle it, detect it, and build whole industries around it. But if someone asks for a comfortable human-scale picture of what a photon really is that leaves no remainder of strangeness, the honest answer is that no such picture fully exists. Our theories are powerful and precise, but our visual imagination was not built for this scale of reality. The photon reveals that understanding does not always mean being able to picture something as if it were a kitchen object. Sometimes understanding means trusting a framework because it works, because it predicts, because it survives experiment, even when the old imagination complains. This is not a defeat for thought, it is a refinement of thought. The history of science is full of moments when a deeper truth first felt impossible because it offended familiar habits. Earth moves, time stretches, matter is atomic, space is curved, light is quantized. The photon stands among those corrections. It reminds us that the world is under no obligation to resemble our first metaphors. There is also a more personal lesson in it. Every visible memory you have depends on photons, every face recognized, every page read, every road crossed, every star noticed, every shadow on a wall, every colour associated with a season or a place or a person. The photon is not only a clue about remote physics, it is built into the structure of your ordinary life. It links the grand and the familiar with very little fuss. A photon born in a distant source can end in the chemistry of your retina and become part of a thought. That is not sentimental. It is the actual route by which the visible universe reaches you. And perhaps that is the deepest thing it reveals. Reality is not divided cleanly into a human world over here and a cosmic world over there. The same physics runs through both. The sunlight on a table, the signal in a fibre optic cable, the glow of a city at night, the spectrum of a star, the working of an eye, the test of quantum theory, all belong to one connected account. The photon is small enough to belong to quantum theory, and common enough to belong to breakfast. Very few things make that crossing so gracefully. So when we ask what a photon reveals about reality, the answer is not one neat slogan. It reveals that the world is made of fields as well as things, that empty space is structured, that energy can be discrete, that observation is interaction, that relation can be fundamental, that large-scale smoothness can emerge from tiny events, that light is both a messenger and a participant, and that our best understanding of nature often requires better concepts than the ones daily life first handed us. That is a lot to learn from something you cannot hold in your hand, And still the photon keeps moving through the world without seeming burdened by any of these philosophical consequences. It leaves stars, crosses space, glances off water, warms stone, enters leaves, triggers detectors, reflects from windows, scatters in air, and disappears into eyes. It does all the ordinary work of being light, while also carrying one of the most persistent messages in modern science, which is that reality is not less real than we thought, only less familiar. The deeper we look, the less the universe resembles a collection of tiny visible objects arranged in a blank box, and the more it resembles a structured web of fields, quanta, interactions, and lawful surprises. And perhaps that is the right place to leave the photon for now, not pinned down, not reduced to a toy image, but doing what it has been doing all along, arriving from the world, crossing the room, crossing the sky, and making reality visible a little at a time.